Imagine lying back in your favorite chair, closing your eyes for a moment, and letting your mind drift beyond the walls of your home, beyond the familiar skies above, far past the clouds, the moon, and even the distant sun. Out there, somewhere in the endless stretch of the cosmos, are worlds that no human has ever walked on, oceans we have yet to explore, skies we have yet to touch. Tonight, or perhaps in the quiet of tomorrow morning, you are invited to take a journey not through time alone, but through possibility. Humans have always looked up. For millennia, our ancestors traced the paths of the stars, created stories about the planets, the sun, the moon, and the occasional wandering comet. These were not just tales. They were whispers of curiosity, an innate longing to understand where we are and perhaps where else we could be. That longing never disappeared. It evolved. In our age, we have sent machines across the solar system, captured images of planets circling distant suns, and discovered that the universe is far larger and far stranger than we ever imagined. But the question remains, could we, one day, leave our blue planet and make our home somewhere else? Could humans not just visit, but truly live on another world? With skies that may be different shades, air that may feel unfamiliar, and landscapes that stretch beyond anything we know. Tonight, let's explore this dream together. No rush, no pressure, just curiosity and wonder. The thought might feel strange at first. The Earth has been our home for thousands of generations. It has oceans that rise and fall, forests that breathe life, deserts that shimmer in the sun. It is beautiful, familiar, and yet, perhaps limited. For every miracle Earth provides, there is also risk: storms, earthquakes, heat waves, cold nights. And as our population grows, our cities expand and our resources strain. The idea of looking outward beyond our planet becomes not just a fantasy, but a question of survival tonight. As you listen, allow yourself to imagine stepping onto a world entirely unlike our own. A world where the ground beneath your feet is colored in shades you have never seen, where the air tastes slightly different, where the horizon curves in unfamiliar ways. Imagine waking up to twin suns or standing on the edge of an ocean that glows with bioluminescent light under a strange sky. The universe is vast and possibilities are endless. From ancient myths to modern science fiction, the allure of other worlds has always fascinated humans. Ancient Greeks spoke of the wandering stars, planets that moved across the sky, gods in disguise. Renaissance thinkers dreamed of lunar landscapes and Martian civilizations. And today, authors, filmmakers, and scientists alike imagine not only visiting other worlds, but living on them, building cities, growing food, raising families, and shaping societies that may thrive where Earth cannot. But what is it that drives this fascination? Perhaps it is the simple truth that humans are explorers. We have always been. Our earliest ancestors crossed continents, navigated oceans, and climbed mountains in search of new horizons. The stars represent the next frontier, a realm where we have yet to leave a footprint. This fascination also carries a hint of longing and acknowledgement that life on Earth, for all its beauty, is not eternal. The sun will age, the climate will shift, and one day, Earth itself may not be able to sustain life as we know it. Thinking about other planets is not just escapism. It is a form of preparation, a vision of hope for future generations. Tonight, we will not rush to answers. Instead, we will wander slowly through the possibilities. Which worlds could sustain human life? Which may be inhospitable? Could some planets even be better than Earth, with climates more stable, landscapes more forgiving, or resources more abundant? These questions do not have simple answers. And that is precisely why they are worth exploring. As you continue to listen, allow yourself to relax further. Breathe slowly. Picture the stars, the endless stretches of darkness pierced by glimmers of light. Picture yourself floating in space, looking back at the tiny, vibrant orb of Earth, feeling both awe and curiosity. This is a safe journey. You will not be leaving your home physically tonight, but your mind. Your imagination will travel farther than it ever has before. In the next sections, we will explore what makes a planet habitable, which worlds could one day host human life, and how we might overcome the immense challenges of living beyond Earth. We will discuss science, technology, dreams, and the sheer wonder of possibility. So, close your eyes for a moment, or keep them softly focused, and let your mind drift outward. The journey begins here, not with rockets or machines, but with curiosity and with the timeless human dream to step onto another world and call it home. As we continue our journey through the stars, it is important to pause and ask a fundamental question. What exactly makes a planet capable of supporting life, especially human life? After all, not every world we see shining in the night sky is a potential home. Some are scorching balls of rock, others frozen wastelands, and some are nothing more than clouds of gas swirling aimlessly in space. At the heart of habitability lies a combination of delicate factors that must align in just the right way. One of the most critical is atmosphere. Our own planet, Earth, is encased in a thin layer of gases that does more than just allow us to breathe, that regulates temperature, protects us from harmful radiation, and creates weather systems that sustain life. Without the right mix of gases, a planet could be deadly, no matter how appealing it might look from afar. Imagine stepping onto a world where the air cannot sustain human life, where every breath burns your lungs. Even if water flows there and the sun shines, it would still be uninhabitable. Another key factor is temperature. Earth resides in what scientists call the Goldilocks zone, a distance from the sun that is not too hot and not too cold, where water can exist as a liquid. Liquid water is the foundation of life as we know it, from the smallest bacteria to the largest mammals. Without it, life struggles to take hold. But the Goldilocks zone is not just about warmth, it is about balance. Too close to a star and the planet is scorched. Too far and it freezes into a lifeless ice ball. Temperature is intimately tied to a planet's atmosphere, its orbit, and even its geological activity. Water itself is another essential ingredient, and not just any water. Clean, accessible water in sufficient quantity is crucial for survival. On Earth, water cycles through rivers, clouds, oceans, and ice in a dynamic system that supports life. On another planet, the presence of water could determine whether human colonies could thrive or merely survive. Scientists also consider gravity as an important factor. Life on Earth evolved under a specific gravitational pull, and our bodies are adapted to that. Too low, and bones and muscles weaken. Too high, and every movement becomes a struggle. Gravity affects blood flow, organ function, and even reproduction, meaning it is more than just a matter of comfort, it's a matter of survival. Finally, radiation is an invisible but deadly threat. Our planet's magnetic field shields us from solar and cosmic radiation, allowing life to flourish on the surface. On a planet without such protection, radiation could quickly become fatal, damaging DNA and causing illnesses over time. In short, a habitable planet is a rare combination of atmosphere, temperature, water, gravity, and protection from cosmic hazards. Each factor alone is important, but together they create the conditions that allow life, and perhaps humanity, to flourish, to understand habitability beyond Earth. Scientists often look inward at life in extreme conditions right here on our own planet. Extremophiles are organisms that thrive in environments once thought uninhabitable. Boiling hot springs, frozen tundras, acidic rivers, and deep ocean trenches. They teach us that life is far more adaptable than we might have imagined. Consider thermophiles, which survive in temperatures exceeding 80 degrees Celsius, or psychrophiles, which live in freezing waters of Antarctica. There are bacteria that endure high radiation levels, fungi that flourish in extreme dryness, and microbes that thrive hundreds of meters below the ocean floor in complete darkness and crushing pressure. These resilient forms of life expand our understanding of what environments could potentially support life by studying extremophiles. Scientists have started to ask, could life survive on Mars under its cold, thin atmosphere? Could organisms exist in the icy oceans beneath the crusts of Europa or Enceladus, moons orbiting Jupiter and Saturn? Could the atmosphere of Venus, dense and acidic, harbor floating microbes high in its clouds where temperatures are milder? These questions are more than theoretical exercises. They guide how we search for life beyond Earth and inform our understanding of habitability. They also remind us that life is not fragile, adapts, evolves, and endures. As we think about human colonization, extremophiles hint at the resilience we must cultivate. If microscopic organisms can survive extreme conditions, could humans, with the aid of technology and preparation, also thrive in worlds once deemed impossible? The search for habitable worlds has taken a dramatic leap in recent decades thanks to the discovery of exoplanets, planets that orbit stars beyond our own sun. Thousands of these distant worlds have been detected, each offering a unique glimpse into the vast possibilities of the universe. Some are gas giants, many times the size of Jupiter. Others are small, rocky worlds similar to Earth. Among them, a precious few reside in. Their stars Goldilocks zone the region where conditions might allow liquid water to exist. Planets like Kepler 186f and Kepler 442b have captured the imagination of both scientists and the public. Kepler 186f is roughly the size of Earth and orbits within the habitable zone of its star. WHILE Kepler 442b is slightly larger and may offer a stable environment for life. These discoveries show us that planets with potentially favorable conditions are not just a dream. They are real, measurable, and increasingly understood. But identifying an exoplanet in the Goldilocks zone is only the beginning. Scientists must determine the planet's atmosphere, its chemical composition, its potential for water, and other factors that influence habitability. Advanced telescopes, both in space and on Earth, are helping us peer deeper into these alien worlds, measuring atmospheres, analyzing light spectra, and searching for biosignatures, chemical signs that life might exist there. The Goldilocks zone is a useful guide, but it is not the final word. As we learn from extremophiles and the surprising diversity of life on Earth, it becomes clear that life could exist beyond this zone under the right conditions. Some planets might be cold, yet contain liquid water beneath their icy crusts. Others might orbit stars very different from our Sun, with unique chemistry that could support life in unfamiliar ways. By combining our understanding of planetary conditions, extremophiles, and exoplanet discoveries, we begin to build a framework for habitability. This framework is not only a map of where life could exist, it is a blueprint for where humans might one day live. And as we will explore in the next sections, understanding these conditions is the first step toward imagining the practical realities of life beyond Earth. As we look deeper into the cosmos, the question of habitability becomes both more exciting and more complex. Every planet and moon is unique, with its own environment, chemistry, and history. Some worlds are bathed in constant sunlight, while others are locked in eternal darkness. Some spin so slowly that one side faces their star for centuries at a time, while others whirl at dizzying speeds. Each of these conditions shapes the potential for life and the possibilities for human habitation. Understanding these differences is essential if we ever hope to step foot beyond our own world. Consider Mars, the planet that has captivated scientists and dreamers alike for decades. Its surface is cold and dry, its atmosphere thin and composed mostly of carbon dioxide. Dust storms rage across its plains, and radiation from the sun reaches the surface unimpeded by a protective magnetic field. At first glance, Mars may seem inhospitable, even hostile. Yet it remains our closest target for human colonization, in part because of its accessibility, but also because it holds the promise of adaptation. Beneath its surface may lie water ice, and possibly, long ago, rivers and lakes. Human ingenuity may one day transform these challenges into opportunities, allowing settlements to thrive beneath domes or underground, shielded from the harsh environment beyond our solar system. The variety of exoplanets discovered in recent years has expanded our understanding of what might be possible. Some of these planets orbit stars much smaller than our Sun, casting dim light over their surfaces. Others circle bright, massive stars, where heat and radiation create conditions very different from anything on Earth, planets that seem inhospitable. At first may still harbor the necessary ingredients for life for human habitation. With the right technologies, for example, a planet with a dense atmosphere could trap heat and protect inhabitants from radiation, even if it is farther from its star than Earth is from the Sun. The balance of factors is intricate and often surprising. Gravity, something we take for granted on Earth, is another critical consideration. Human bodies have evolved under the constant pull of Earth's gravity, and any significant deviation could have profound effects on muscles, bones, and internal organs. Long-term exposure to low gravity, such as that on Mars, could weaken bones and muscles, alter circulation, and affect overall health. Scientists are already studying astronauts who have spent months in microgravity on the International Space Station to understand these changes. And they are exploring ways to mitigate the risks. Artificial gravity, exercise regimes, and carefully designed habitats may one day allow humans to thrive in environments that were once thought impossible. Atmosphere is equally crucial. The mix of gases, the pressure, and the presence of protective layers all determine whether humans could survive on a planet's surface without heavy life support systems. Earth's atmosphere provides a perfect balance of oxygen, nitrogen, and trace gases, along with a protective shield against harmful radiation. Without this, survival would require either full suits, closed habitats, or even the generation of artificial atmospheres within controlled environments. Scientists are studying ways to create these environments efficiently, using technologies such as pressurized habitats, oxygen generation systems, and chemical scrubbing of carbon dioxide. Water, the foundation of life, is often the decisive factor in determining habitability. Liquid water is essential not only for drinking, but for growing food and supporting ecosystems. On Earth, water cycles through oceans, rivers, and the atmosphere, creating a dynamic and life-sustaining system. On other planets, water may be hidden beneath ice, trapped in minerals, or flowing in underground oceans. Locating and harnessing these sources is a key step in planning for human habitation. Technologies such as drilling, water extraction, and purification systems may allow future colonists to use what is available, even if it is scarce or difficult to access. Radiation, invisible but deadly, presents another challenge. Beyond Earth's protective magnetic field, cosmic and solar radiation can damage DNA, increase cancer risk, and interfere with electronics. On planets without strong magnetic fields, humans would need shields, protective habitats, or other technological solutions to stay safe. Some ideas include underground settlements, water or ice barriers, and advanced materials designed to absorb or deflect radiation. Even small steps, such as careful scheduling of outdoor activity, could make a significant difference in survival and long-term health. Our understanding of habitability is constantly evolving, shaped not only by observations of distant worlds, but by discoveries on our own planet. Life is remarkably adaptable, and this adaptability gives hope that humans may also adapt with assistance from technology to worlds far different from Earth. Each new exoplanet discovered challenges our assumptions, expanding the possible range of environments where life could exist. Some may be too cold, too hot, or too acidic for humans to survive naturally. Yet with domes, habitats, and life support systems, even these worlds could become potential homes. This exploration also forces us to consider timescales. Planets are not static. Their atmospheres, temperatures, and surfaces change over millions or billions of years. A planet that seems inhospitable today may once have been fertile, or may become so in the distant future. Conversely, Earth itself has undergone dramatic shifts over its long history, reminding us that habitability is not guaranteed, even on our home planet. Understanding the dynamic nature of planets allows us to make more informed predictions about where humans could live and how we might prepare for the challenges ahead. In essence, understanding habitability requires both imagination and rigor. We must combine careful observation, data collection, and theoretical modeling with the ability to envision life in conditions entirely unlike those on Earth. It is a delicate balance between science and curiosity, between the known and the possible. And as we continue our journey, this understanding becomes the foundation for imagining human colonies on other worlds, guiding the choices we make, the technologies we develop, and the dreams we pursue. As we continue to explore habitability, it becomes clear that no single factor determines whether a planet could support humans. Instead, it is the interplay of many elements: temperature, atmosphere, water, gravity, radiation, and resources that creates the conditions for life. Each new discovery in our solar system and beyond adds pieces to this intricate puzzle, allowing us to imagine not just survival, but thriving. On worlds far different from our own, Mars, our most discussed neighbor, offers a fascinating case study. Its red deserts stretch for thousands of kilometers. Ancient riverbeds hint at a wetter past, and ice is present at the poles and just below the surface in many regions. While the planet is cold, with an average temperature of around -60 degrees Celsius, and its atmosphere is thin, technology could make life possible. Habitats might be built underground to protect from radiation and dust storms. Greenhouses could grow food using hydroponics, recycling water, and nutrients efficiently. In this sense, Mars is not just a target for exploration, it is a laboratory for understanding how humans could adapt to new worlds beyond Mars. Moons, such as Europa and Enceladus, captivate scientists with the promise of hidden oceans beneath icy crusts. While these oceans are shielded from sunlight and the surface conditions are extreme, the liquid water beneath could harbor life or even support human colonies in floating or submerged habitats. Imagine a domed city beneath the ice, illuminated by artificial light, where humans explore alien oceans with robotic companions. The technology to achieve this is still in development, but it is no longer purely science fiction. These icy moons show us that habitability is not limited to planets with familiar landscapes or Earth-like atmospheres. Life may exist in forms and places we have yet to imagine. Exoplanets add even more layers of possibility. Worlds like Kepler-4 b and Proxima Centauri b orbit stars far different from our Sun, presenting conditions that challenge our understanding of habitability. Kepler-4 b, slightly larger than Earth, lies within the habitable zone of its star, potentially offering stable temperatures and the possibility of liquid water. Proxima Centauri b orbits a red dwarf, a star smaller and cooler than our Sun, which may expose the planet to frequent stellar flares. Each of these scenarios requires innovative solutions for human adaptation. From radiation shields to climate-controlled habitats, gravity remains a constant concern. Mars has about 38% of Earth's gravity, which could lead to muscle atrophy and bone density loss over time. Low-gravity environments might also affect circulation and organ function. On the other hand, A planet with stronger gravity than Earth could make movement and labor exhausting. Scientists are exploring methods such as artificial gravity in rotating habitats and rigorous exercise protocols to mitigate these effects, ensuring humans can not only survive but maintain health over generations. Resources, often overlooked in discussions of habitability, are also critical. Mining for water, oxygen, and minerals will be essential for sustaining colonies. Plans for Mars and other potential settlements involve extracting ice, converting it into drinking water and breathable oxygen, and using local materials to construct habitats. In exoplanet scenarios, remote sensing and robotic exploration will likely precede human arrival. Mapping the surface, identifying resource-rich areas, and assessing risks. Efficient use of resources is not just a matter of convenience, it is a matter of survival in worlds where every drop of water, every kilogram of material, is precious. Another consideration is the psychological and social aspects of living on another world. Isolation, confined spaces, and distance from Earth could create challenges for mental health and social cohesion. Lessons from Antarctic stations and long-duration missions on the International Space Station provide valuable insights. Regular communication with Earth, community-building activities, and thoughtfully designed habitats can help maintain morale and mental well-being. In this sense, habitability is not just about physical survival, it's about creating environments where humans can thrive emotionally, socially, and culturally. Technology, in all its forms, becomes our bridge between imagination and reality. Life support systems, advanced robotics, artificial ecosystems, and sustainable energy sources will be the pillars of any off-world settlement. Solar panels could harness the energy of distant suns. Nuclear reactors could provide steady power, and recycled materials could reduce dependency on Earth. Every technological breakthrough brings us one step closer to making the dream of living beyond Earth a tangible reality. Finally, as we consider habitability, it is important to embrace the unknown. The universe is vast, and our understanding of life, biology, and adaptation is still limited. Planets we once dismissed as uninhabitable may harbor hidden oceans, protective atmospheres, or chemical conditions that allow life to flourish. Conversely, worlds that seem promising may present unexpected dangers. Curiosity, careful observation, and a willingness to explore the limits of possibility are essential. By combining knowledge of planetary conditions, lessons from extremophiles, discoveries of exoplanets, and advancements in technology, we begin to see a future where humans might live beyond Earth. This understanding lays the foundation for imagining not just survival, but a rich and diverse life among the stars. The universe is not a distant dream. It is a landscape of possibilities, waiting for the human imagination to explore, adapt, and perhaps one day call home. As we turn our gaze from the general principles of habitability to specific worlds, the question becomes both more exciting and more tangible. Which planets or moons could humans realistically inhabit one day? While countless stars in the universe host planets, only a select few appear to hold the potential for human life. Even among these, the challenges are immense. But the possibilities are tantalizing. Mars, often called the Red Planet, is our closest neighbor and the most frequently discussed candidate for human colonization. Its surface is rocky and barren, with vast deserts stretching for thousands of kilometers, ancient riverbeds hinting at a wetter past, and ice deposits at the poles and beneath the surface. The atmosphere is thin, composed mostly of carbon dioxide, and provides little protection from cosmic radiation. The planet is cold, with an average temperature around -60 degrees Celsius, and dust storms can sweep across its surface, lasting for weeks. Yet, despite these harsh conditions, Mars offers one of the most accessible opportunities for human settlement. Robotic missions have mapped its surface extensively, identifying potential landing sites and regions with ice deposits that could be converted into water for drinking, agriculture, and oxygen production. with advanced life support systems, radiation shielding, and sustainable energy sources. Humans may one day build habitats under protective domes or even underground, turning these challenges into manageable obstacles. Beyond Mars, moons within our own solar system present intriguing possibilities. Europa, a moon of Jupiter, is covered in a thick shell of ice, beneath which lies a subsurface ocean that could contain more water than all of Earth's oceans combined. While the surface is harsh, cold, and bombarded by radiation, beneath the ice lies a protected environment where life might exist or where human habitats could be constructed. Similarly, Enceladus, a small moon of Saturn, contains geysers that spew water and organic compounds into space, hinting at a hidden ocean below. These icy moons challenge our understanding of habitability. Life may not require a sunny, Earth-like surface, but could flourish in hidden, shielded environments where warmth and liquid water exist beneath the ice. Human colonization of these moons would require advanced technologies, from drilling and tunneling to constructing pressure-resistant habitats and generating energy in environments far removed from sunlight, even further afield. Exoplanets orbiting distant stars offer a wealth of potential, though the challenges increase dramatically with distance. Planets such as Kepler-4 to be roughly 33% larger than Earth orbit within their star's habitable zone, where temperatures could allow liquid water to exist. Similarly, Kepler-186f, a planet slightly larger than Earth, lies in the Goldilocks zone of its small, dim star, presenting conditions that may be favorable for life. Proxima Centauri b, orbiting the closest star to our Sun, Proxima Centauri is another candidate. While it may experience stellar flares, it also resides in a zone where liquid water could exist, at least in certain regions or seasons. These planets are far beyond our current reach, requiring travel that could take decades or centuries with existing technologies. Yet they fuel the imagination and guide scientific exploration. Gravity is a crucial consideration for these candidates. Mars has about 38% of Earth's gravity, which could impact human physiology over long periods. Kepler-4 slightly larger than Earth, may have a gravity similar to or slightly stronger than ours, affecting how humans move, work, and adapt. Proxima Centauri b's mass and radius are less precisely known, but understanding these factors will be essential for planning any future settlement. Gravity influences muscle strength, bone density, circulation, and even reproduction. So each potential world demands careful consideration and preparation. Atmosphere is equally important. On Mars, the thin atmosphere means humans cannot breathe naturally, requiring enclosed habitats or spacesuits for survival. The icy moons may have no breathable atmosphere at all, necessitating pressurized domes or underwater habitats. Exoplanets may vary dramatically. Some could have thick, Earth-like atmospheres, while others may be dominated by gases toxic to humans. Understanding each planet's atmospheric composition, pressure, and protective qualities against radiation will be essential before considering colonization. Water, the lifeblood of habitability, is central to evaluating these candidates. Mars has water ice, and potential briny liquid flows in certain regions. Europa and Enceladus contain subsurface oceans that could provide not only drinking water but potential resources for food and industrial processes. Exoplanets in the habitable zone may harbor oceans, lakes, or rivers, though direct confirmation is still beyond our current observational capabilities. Future telescopes and space missions will aim to detect these vital signs, searching for chemical signatures and liquid water that could support human life. Radiation protection is another major concern. Mars lacks a strong magnetic field, exposing its surface to harmful solar and cosmic radiation. Europa and Enceladus, while shielded beneath ice layers, would require careful habitat design to ensure safety. Exoplanets, particularly those orbiting active stars, may present radiation challenges that exceed those found within our solar system. Solutions might include constructing underground habitats, utilizing ice or water as shielding, and developing advanced materials capable of absorbing or deflecting radiation. Resource availability, often overlooked, is vital for sustaining human life. Mars has regolith, rich in minerals, ice that can be converted into water and oxygen, and potential sunlight for solar energy. Europa and Enceladus may offer water and chemical compounds needed for life support, though energy sources must be engineered carefully. Exoplanets remain largely unknown in this regard, emphasizing the need for preliminary robotic missions and remote sensing to assess resource availability before committing to human colonization. The potential for better than Earth worlds adds another layer of excitement. Some exoplanets may have more stable climates, richer resources, or less violent weather than our home planet, while Earth remains uniquely suited for life. Imagining these alien worlds challenges us to think beyond familiar parameters, to envision new ecosystems, landscapes, and lifestyles that could redefine the human experience. The idea that a planet might surpass Earth in comfort or habitability is both thrilling and inspiring, inviting humanity to dream bigger, plan carefully, and embrace the possibilities that await among the stars. Finally, the human spirit, curiosity, ingenuity, and resilience is perhaps the most important factor in considering candidate planets. Technology, preparation, and imagination may allow humans to thrive in places that at first seem inhospitable. From domed cities on Mars to underwater habitats on icy moons. From distant exoplanets with unknown challenges to artificial colonies in orbit. The potential candidates for human habitation inspire not only scientific research, but wonder and hope. Each world represents a unique story, a new chapter in humanity's journey, and a tangible possibility for life beyond Earth. As we continue examining candidate worlds for human habitation, it becomes clear that each presents a unique set of opportunities and challenges. Mars, for instance, is within reach with current and near-future technology, making it the most practical first step for interplanetary colonization. Its proximity allows for resupply missions from Earth, emergency evacuations, and a shorter communication delay compared to distant exoplanets. Its surface, though harsh, offers ample sunlight for solar power, regions with water ice for life support, and a solid ground for constructing habitats. However, the thin atmosphere and low gravity demand innovative solutions for protection and long-term health. Dust storms, which can cover the entire planet for weeks, pose challenges to energy generation, transportation, and daily operations. Scientists and engineers are actively designing domed cities, underground habitats, and self-sufficient life support systems to overcome these obstacles. Europa and Enceladus. The icy moons of Jupiter and Saturn present more extreme challenges, but equally fascinating possibilities. Their subsurface oceans could harbor life or provide water for human use. But accessing these hidden resources requires drilling through kilometers of ice and constructing habitats capable of withstanding immense pressure and cold. Energy is another concern. Sunlight barely reaches the icy surface, so alternative sources like nuclear power or geothermal energy from tidal forces would be necessary. Despite these hurdles, the potential for discovering life and sustaining human colonies in such unique environments is compelling. The idea of living under the ice, exploring alien oceans, and observing otherworldly landscapes would redefine our experience of what a home in space could. Exoplanets introduce a new level of complexity and excitement. Kepler-4 for to be Kepler-1, 86F, and Proxima Centauri b are all within their star's habitable zones, where temperatures might allow liquid water to exist. Yet their vast distances make human travel a monumental challenge, potentially requiring decades or even centuries with current propulsion technology. These planets may offer conditions superior to Earth in some ways, less extreme weather, more stable climates, or even more abundant resources, but they remain largely uncharted territories. Before humans can even consider setting foot on these worlds, robotic missions, advanced telescopes, and extensive remote sensing will be essential to understand their atmospheres, surface conditions, gravity, and potential hazards. Gravity, again, plays a crucial role in determining how humans might adapt to new worlds. Mars' lower gravity may cause muscle atrophy, bone loss, and cardiovascular changes over time. Artificial gravity solutions, such as rotating habitats that simulate Earth-like gravity, could help mitigate these effects. Exoplanets slightly larger than Earth might have stronger gravity, which could make movement more strenuous and daily activities more demanding. Scientists must consider not only the immediate effects on human physiology, but also long-term impacts on reproduction, growth, and overall health. Selecting candidate worlds requires balancing these gravitational factors with other aspects of habitability to ensure the best chances of sustainable human life. Atmospheric conditions on candidate planets vary widely. Mars has a thin carbon dioxide-rich atmosphere, necessitating enclosed habitats and spacesuits for survival. Europa and Enceladus may have virtually no breathable atmosphere, meaning humans would rely entirely on pressurized, life-supporting environments. Exoplanets could present everything from Earth-like air to toxic or corrosive atmospheres, influencing the design of habitats, suits, and emergency protocols. Understanding these conditions is critical. The right atmosphere, the technology to simulate one could mean the difference. Between thriving and merely surviving, water remains the cornerstone of habitability. Mars has frozen water at its poles and in underground layers, potentially convertible for human use. Europa and Enceladus offer vast subsurface oceans, though accessing them requires innovative engineering solutions. Even distant exoplanets may harbor liquid water, but conformation remains a challenge. Technologies for extracting, purifying, and distributing water will be crucial, and successful management of this resource will likely dictate the feasibility and longevity of human colonies. Radiation protection is equally critical. Mars lacks a magnetic field, leaving its surface exposed to solar and cosmic radiation. Europa and Enceladus are partially shielded by their ice layers, but habitats must still account for cosmic rays and potential energetic particles from their parent planets. Exoplanets may orbit active stars, posing additional risks. Solutions might include underground living spaces, water and ice shielding, or advanced materials capable of deflecting harmful radiation. Without such measures, prolonged exposure could lead to severe health consequences. Underscoring the importance of integrating protection into every aspect of habitat design, resources extend beyond water. Minerals, metals, and elements necessary for construction, agriculture, and technology are critical for sustaining human life. Mars offers regolith, rich in minerals, while Europa and Enceladus may provide water and chemical compounds useful for life support and energy generation. Exoplanets, however, are largely unknown in this regard, emphasizing the need for preliminary robotic exploration to identify viable locations for future colonies. Efficient use of local resources will be essential, reducing dependence on long and costly supply lines from Earth. Psychological and social factors also shape habitability. Isolation, confinement, and distance from Earth can create mental and emotional challenges. Studies of astronauts in long-duration missions and Antarctic researchers highlight the importance of community, structured schedules, recreation, and communication with loved ones. Future colonists will need not only physical protection, but also environments designed to support mental health, social interaction, and a sense of purpose. Designing such habitats will be as important as shielding them from the cold, radiation, or thin atmosphere. In addition to survival, the concept of thriving should guide our vision. Candidate planets may offer the chance to create entirely new forms of human experience, with landscapes, climates, and ecosystems unlike anything on Earth. From domed cities on the Martian plains to underwater colonies beneath Europa's ice. Humans may adapt and innovate, creating vibrant societies in places once thought uninhabitable. These worlds challenge us to reconsider what home means, to imagine life beyond familiar terrains and familiar skies, and to embrace the full potential of human ingenuity and resilience. Finally, every candidate world carries a sense of mystery. Even as we map, measure, and analyze, unknowns remain. Hidden oceans, unexpected weather, unanticipated geological activity, or even unknown forms of life. This uncertainty is part of the allure, fueling exploration, scientific inquiry, and imagination. Each candidate, planet, or moon offers a story waiting to unfold, a challenge to meet, and a potential new chapter in the saga of humanity among the stars. As we move toward practical strategies for human habitation, it becomes evident that technology will be the bridge between imagination and reality. No matter how promising a candidate planet or moon may seem, without innovative solutions, humans cannot thrive beyond Earth. For Mars, one of the most immediate targets, technology must address life support, radiation protection, energy production, and sustainable food systems. Habitats will likely combine domed cities on the surface with underground complexes that shield inhabitants from cosmic rays and Martian dust storms. Solar power will harness the sunlight, and nuclear reactors could provide a steady energy supply during long periods of darkness. Hydroponic and aeroponic farms could generate fresh food using minimal water, while recycling systems ensure that air, water, and waste are efficiently managed. The icy moons, Europa and Enceladus, challenge engineers and scientists to think differently. Accessing subsurface oceans requires drilling through kilometers of ice and constructing pressure-resistant habitats capable of supporting life in extreme cold. Energy production might rely on tidal forces, geothermal heat, or compact nuclear systems. Living beneath the ice could provide natural radiation protection, but habitats must also manage temperature, pressure, and resource distribution carefully. Robotic exploration would precede human arrival, mapping the ice, monitoring ocean currents, and detecting potential hazards or resources. These strategies transform previously uninhabitable moons into potential laboratories for sustainable off-world living, demonstrating humanity's capacity to adapt in even the most alien environments. For exoplanets like Kepler 442b, Kepler 186f, or Proxima Centauri b, the challenges multiply due to distance. Travel could take decades or centuries, requiring spacecraft capable of long-term life support, resource recycling, and propulsion efficiency. Colonists may need to be multi-generational, with entire communities living in space en route to their destination. Upon arrival, habitats would be designed to adapt to local conditions, whether that means constructing domed cities, underground refuges, or floating platforms in oceans. Advanced robotics would assist in construction, resource extraction, and ongoing maintenance, ensuring that humans can focus on exploration, research, and community building. Artificial ecosystems will play a critical role in long-term habitability. Closed-loop systems that recycle air, water, and nutrients mimic Earth's biosphere, providing sustainable environments for food production and waste management. These ecosystems can also contribute to mental health, offering greenery, water features, and simulated weather patterns that maintain a sense of connection to Earth, even on worlds with seemingly abundant resources. Artificial ecosystems provide a safety net, ensuring stability and resilience in unpredictable conditions. Long-term colonization requires careful consideration of social structures and human behavior. Isolation, extreme environments, and dependence on technology pose unique challenges to mental health and societal cohesion. Community design, recreation, communication with Earth. And structured schedules become as important as air, water, and food. Lessons learned from Antarctic stations, submarines, and space missions highlight the importance of creating supportive, interactive, and purposeful communities. Social well-being may determine whether a colony merely survives or truly thrives. Resource utilization is another crucial factor. Mars offers mineral-rich regolith, water, ice, and sunlight. Europa and Enceladus provide water, salts, and potentially chemical compounds useful for life support. Exoplanets may hold untapped resources, but identifying and extracting them will require extensive scouting and robotic assistance. The ability to use local materials reduces dependence on Earth, increasing the feasibility of permanent settlements and opening the door to larger, self-sufficient communities. Radiation protection continues to be a central concern. Solutions may include building habitats underground, using water or ice as shields, and employing advanced materials capable of absorbing or deflecting harmful particles. In the long term, understanding and manipulating magnetic fields or developing planetary-scale protection systems could extend safe living zones beyond what was once thought possible. These measures will allow humans not only to survive, but to explore and expand across alien landscapes safely. Exploration and adaptation will also redefine the human experience. Imagine walking through a Martian valley under a protective dome, observing dust storms at a distance while tending a hydroponic farm. Picture submersible vehicles exploring Europa's ocean beneath kilometers of ice, discovering alien life or simply marveling at the beauty of an uncharted world. Consider the thrill of navigating an exoplanet with climates and terrains unlike anything on Earth. Using robotics, AI, and human ingenuity to transform the environment into a habitable space. These scenarios are not mere fantasies, they are plausible visions grounded in science, technology, and the indomitable human spirit. The question of sustainability extends beyond survival. Energy generation, waste management, food production, and habitat construction must all be designed for efficiency, resilience, and long-term stability. Solar, nuclear, and geothermal power could provide energy, while advanced recycling systems ensure minimal waste. Agriculture may rely on genetically optimized crops or lab-grown proteins to reduce resource demands. The interplay of technology, biology, and human creativity will determine whether colonies can flourish over decades or centuries, transforming harsh alien worlds into vibrant, self-sustaining communities. Ultimately, the candidates for human habitation, Mars, Europa, Enceladus, and distant exoplanets represent both challenges and opportunities. Each world tests our ingenuity, adaptability, and resilience, pushing humanity to rethink what it means to live, work, and thrive beyond Earth. The journey to these worlds is not only about survival, but about redefining the human experience, creating new societies, and expanding our presence in the cosmos. Every technical hurdle, environmental challenge, and unknown variable is a chance to learn, innovate, and dream bigger as we explore these worlds. We are reminded that human habitation is as much a mental and cultural challenge as it is a physical one. Our ability to imagine life on alien worlds, to design habitats that support both body and mind, and to build societies capable of enduring isolation and adversity will ultimately determine our success. The planets and moons themselves are the stage, but it is human curiosity, resilience, and creativity that will write the story of life beyond Earth. In this way, the journey to candidate planets for human habitation is not just a scientific endeavor, it is a profound exploration of what it means to be human. Each step forward, each new technology, and each successful mission brings us closer to realizing the dream of life among the stars. From Mars' red deserts to Europa's icy oceans and distant exoplanets orbiting alien suns, the universe offers endless possibilities. With preparation, ingenuity, and determination, humanity may one day leave Earth behind, not in desperation, but in pursuit of curiosity, exploration, and the promise of new worlds to call home. As humanity sets its sights on distant worlds, one reality becomes immediately clear. Surviving and thriving on another planet or moon is not simply a matter of arriving. The environments of candidate worlds are extreme, often hostile, and radically different from Earth, from freezing temperatures and toxic atmospheres to high radiation levels and fluctuating gravity. These challenges demand innovative solutions, advanced technology, and careful planning. Overcoming environmental obstacles is not only a test of engineering, but also of human resilience and adaptability. Take Mars, for example. Its thin atmosphere is mostly carbon dioxide, providing virtually no natural protection from cosmic rays and solar flares. Surface temperatures average around -60 degrees Celsius, but can swing dramatically from day to night, creating stress on structures, machinery, and human bodies. Dust storms, some spanning the entire planet, can last for weeks and block sunlight, impacting solar energy generation and visibility. While these conditions might seem insurmountable, human ingenuity is already at work designing solutions. Habitats built with radiation-shielding materials, domes reinforced to withstand dust storms, and underground facilities can provide safe environments. Advanced climate control systems maintain stable temperatures, while robotic support helps with tasks outside protective structures. Radiation is a concern on almost every candidate world. Without Earth's protective magnetic field, humans face increased risks of cancer, genetic damage, and other long-term health issues. Solutions include constructing habitats underground, where the planet's crust acts as a natural shield, or using water, ice, and specialized materials as protective barriers. On icy moons like Europa or Enceladus, living beneath the thick ice offers additional shielding. But habitats must also be designed to endure extreme pressure and maintain warmth. Artificial magnetic shields or wearable radiation protection may become part of daily life, ensuring safety while allowing exploration of these alien environments. Temperature extremes present another major challenge. Mars nights can drop to -100 degrees Celsius, while its equatorial regions can reach near 20 degrees Celsius during the day. Europa's icy surface is far colder, with temperatures below -160 degrees Celsius, while Enceladus is even colder. Life support systems must maintain stable temperatures for human comfort and survival, regulate oxygen levels, and manage humidity. Advanced insulation, heat recycling systems, and energy-efficient climate control technologies are essential. Even exoplanets can pose temperature extremes, depending on their distance from their star, atmospheric composition, and rotation patterns. Every candidate world demands careful study and technological adaptation to make it livable. Gravity, too, affects more than just human physiology. It influences engineering, construction, and daily life. Low-gravity environments, like Mars, 38% of Earth's gravity, can lead to muscle atrophy, bone density loss, and circulation changes. Machinery and infrastructure must account for reduced gravitational forces, while habitats need to ensure human mobility and safety. Conversely, planets with higher gravity than Earth would place additional stress on the human body, requiring reinforced structures, careful design of work routines, and perhaps artificial gravity solutions to maintain long-term health. Water, availability, and management remain central to overcoming environmental challenges. Mars contains ice at its poles and just beneath the surface, while Europa and Enceladus hide oceans beneath layers of ice. Extracting and purifying water from these sources requires advanced drilling, heating, and filtration systems. Water serves not only as a vital resource for drinking, agriculture, and hygiene, but also as a medium for shielding against radiation. Even distant exoplanets may have water, but confirmation and sustainable management are still decades away. Planning for water use, recycling, and distribution is a critical aspect of habitat design and daily life in space. Atmospheric conditions vary dramatically across candidate worlds. Mars' thin, CO-rich atmosphere requires enclosed habitats and oxygen supply, while Europa and Enceladus have virtually no breathable air. Exoplanets may have toxic atmospheres, extreme pressures, or chemical compositions hazardous to humans. Engineering solutions must create reliable, sealed habitats with controlled atmospheres. Life support systems need redundancy and fail-safes to ensure constant supply of breathable air, stable pressure, and temperature control. Failure is not an option when humans are millions or billions of kilometers from Earth. Energy generation is equally essential in hostile environments. Solar power works effectively on Mars, but can be disrupted by dust storms. Nuclear reactors offer steady energy for long-duration missions, while geothermal or tidal energy may be harnessed on moons with internal heat sources. For distant exoplanets, energy solutions may rely on onboard power storage or fusion technologies. Reliable energy is not just a convenience, it is a lifeline, powering habitats, life support systems, communication, and transportation. Environmental hazards extend beyond natural conditions. Meteoroid impacts, surface instability, chemical hazards, and unpredictable weather patterns all pose risks. Monitoring systems, early warning technologies, and autonomous repair robots will be essential. Designing habitats that can absorb shocks, seal breaches, and maintain structural integrity under unforeseen circumstances will allow humans to survive and even thrive in otherwise dangerous environments. The human mind and body must also adapt to environmental stress. Isolation, limited social contact, and confinement in controlled habitats can impact psychological health. Structured routines, recreation, and communication with Earth will be crucial for long-term well-being. Even simple tasks like walking, eating, or socializing must be designed to account for reduced or increased gravity, extreme temperatures, and radiation. Overcoming environmental challenges is not only a matter of survival, it is about ensuring humans can live fully, emotionally and physically, in alien worlds. Finally, every challenge represents an opportunity for innovation. By studying and designing solutions for Mars, Europa, Enceladus, and distant exoplanets, humanity is expanding its technological and conceptual toolkit. Solutions for radiation protection, temperature control, artificial ecosystems, and sustainable resource management will not only make space colonization possible, but may also improve life on Earth, each step forward in overcoming environmental challenges brings us closer to living safely and successfully on another world, turning the dream of interplanetary habitation into a real possibility. As we delve deeper into overcoming environmental challenges, the importance of adaptability becomes increasingly clear. Humans are resilient, but long-term survival on alien worlds demands both physical and psychological adjustments. On Mars, for instance, habitats must be designed to maintain not only life-supporting conditions, but also a sense of normalcy. Temperature control, humidity, air pressure, and oxygen levels must be finely tuned, creating an environment that allows humans to live comfortably despite the harsh external conditions. Advanced insulation materials, thermal regulation systems, and redundant life support networks ensure that sudden environmental changes like dust storms or temperature swings do not threaten the colony. Radiation exposure continues to be one of the most pressing environmental hazards. Mars lacks a magnetic field, and its thin atmosphere offers minimal protection from solar flares and cosmic rays. Solutions include building underground habitats where the planet's crust absorbs harmful radiation, or covering surface structures with layers of regolith, ice, or specially engineered materials. On icy moons like Europa and Enceladus, living beneath kilometers of ice provides natural shielding, But maintaining warmth and structural integrity under extreme pressure requires cutting-edge engineering. Innovative wearable technologies such as radiation-resistant suits or portable shields may allow humans to venture safely outside, while autonomous robots can perform high-risk tasks in the most exposed areas. Water, arguably the most critical resource, requires careful management. Mars has ice deposits and potentially briny flows in certain regions. Extracting this water involves heating, filtration, and storage, while minimizing loss to the environment. On Europa and Enceladus, subsurface oceans offer vast amounts of water. But drilling through thick ice layers and maintaining stable habitats under pressure are significant challenges. Closed-loop water recycling systems, desalination units, and advanced purification technologies will ensure sustainable water supply. Beyond mere survival, water also plays a role in energy generation and radiation shielding, making its careful management a cornerstone of any colonization effort. Food production presents another set of environmental challenges. Traditional agriculture is impossible in the harsh conditions of Mars or icy moons. Hydroponic and aeroponic systems, combined with genetically optimized crops or lab-grown proteins, will provide reliable nutrition. Controlled indoor environments allow regulation of light, temperature, and nutrient delivery, ensuring consistent yields. Energy-efficient LED lighting simulates sunlight, while automated monitoring systems prevent disease or nutrient imbalances. These systems not only sustain human life, but also reduce dependence on Earth for resupply. A critical factor for long-term habitation. Energy generation must be resilient and versatile. Solar power works effectively on Mars during clear days, but dust storms can obscure sunlight for weeks. Nuclear reactors provide consistent energy, while tidal forces or geothermal heat may be harnessed on moons with active interiors. For exoplanets far from Earth, energy storage and transport solutions are critical. Redundant systems, including solar, nuclear, and possibly fusion energy, ensure that habitats remain powered even when external conditions fluctuate or unexpected challenges arise. Energy resilience is central to survival, supporting life support, food production, communication, and mobility. Gravity adaptation is a subtle but profound challenge. Mars' low gravity affects muscle strength, bone density, and cardiovascular health. On larger exoplanets, higher gravity could place excessive stress on the human body. Long-term adaptation may require exercise regimens, resistance training, and artificial gravity solutions, such as rotating habitats that simulate Earth-like conditions. Understanding and managing gravity's effects is essential for physical health, reproductive health, and the overall success of interplanetary colonies. Atmospheric engineering may also be required. Mars' sea-rich, thin atmosphere necessitates pressurized habitats and oxygen supply. While some exoplanets may have dense, toxic atmospheres, life support systems must constantly regulate pressure, oxygen levels, and air quality. Redundant monitoring ensures that even minor leaks or malfunctions are quickly corrected, preventing catastrophic failure. In some cases, terraforming or localized atmospheric modification may become a long-term goal, gradually creating more Earth-like conditions and expanding livable areas. Psychological adaptation is as important as physical survival. Isolation, confinement, and separation from Earth can lead to stress, anxiety, and depression. Structured routines, recreation, social interaction, and communication with Earth are essential. Habitats should include communal spaces, exercise areas, and green zones that mimic Earth's natural environments. Virtual reality may supplement physical environments, providing immersive experiences of Earth's landscapes or cultural events. Maintaining mental health ensures that colonists remain productive, cooperative, and capable of facing the unique challenges of alien worlds. Environmental unpredictability requires flexible planning. Dust storms on Mars, unexpected ice shifts on Europa, or extreme weather on exoplanets demand rapid response systems. Autonomous robots, drones, and AI monitoring can detect threats early, perform repairs, and assist human operators. Habitats designed for modular expansion or emergency sealing provide resilience against sudden changes. Contingency protocols, simulation training, and redundancy in critical systems are key to ensuring survival when environments behave unpredictably. Long-term, sustainability also involves resource management. Recycling of air, water, nutrients, and waste is crucial. Mining and processing of local materials reduces dependence on Earth and enables expansion of habitats. Energy-efficient technologies and closed-loop systems minimize resource depletion. Even the psychological and social environment benefits from sustainability, as stable, reliable access to resources fosters confidence, reduces stress, and supports a thriving community. Finally, environmental challenges are opportunities for innovation. Each obstacle: radiation, temperature extremes, gravity variations, limited water, and toxic atmospheres drives technological and conceptual breakthroughs. Solutions developed for alien environments may improve life on Earth. From advanced recycling and water management to energy efficiency and sustainable agriculture, the effort to overcome these challenges is not just survival, it is the extension of human ingenuity into the universe. A testament to creativity, resilience, and the will to explore. By combining advanced technology, careful planning, and human adaptability, the environmental challenges of Mars, Europa, Enceladus, and distant exoplanets can be transformed from insurmountable barriers into manageable realities. In doing so, humanity not only survives beyond Earth, but also thrives, exploring, discovering, and redefining what it means to live on alien worlds. The universe awaits, and with preparation and perseverance, humans may one day inhabit worlds once thought impossible. As we continue exploring how humans can overcome environmental challenges on alien worlds, it becomes increasingly clear that innovation and preparation are our strongest allies. On Mars, Europa, Enceladus, and distant exoplanets, survival is not enough. Colonists must learn to adapt, thrive, and maintain self-sustaining societies. This requires a comprehensive approach combining engineering, biology, social science, and forward-thinking strategies. One of the most critical aspects of adaptation is the integration of advanced life support systems. These systems are more than just oxygen generators or water purifiers. They are complex networks designed to mimic Earth's ecosystems on a miniature scale. Air circulation, humidity control, temperature regulation, and waste management are all interlinked. Any malfunction could cascade into larger problems. So redundancy, real-time monitoring, and autonomous repair capabilities are essential. On icy moons, such as Europa, the extreme cold adds additional strain, requiring habitats to maintain warmth while preserving structural integrity under immense pressure. On exoplanets, unknown atmospheric conditions may require even more sophisticated environmental management, combining sensors, AI, and human oversight to maintain a stable and habitable environment. Another key area of innovation is food production. Hydroponics and aeroponics allow for efficient growth of plants with minimal water and soil, while lab-grown proteins supplement nutrition. On Mars, greenhouses may be designed with thick shielding to protect crops from radiation and dust, while LEDs simulate the necessary light spectrum for photosynthesis. On icy moons, where sunlight is minimal, artificial lighting combined with heat sources from geothermal or nuclear energy becomes crucial. Exoplanets may require fully enclosed, self-regulating ecosystems that combine plant cultivation, insect farming, and microbial food production to sustain human populations over long periods. Energy independence is equally critical. Solar energy works effectively on Mars during clear periods, but dust storms can limit its availability. Nuclear power, including compact fission reactors or even future fusion systems, offers a constant energy supply. On moons with internal heat sources, geothermal or tidal energy could provide supplementary power. Energy storage solutions such as high-capacity batteries or supercapacitors ensure continuous operation of life support systems. Communications and research equipment, even during periods of environmental disruption. Without reliable energy, even the most advanced habitat cannot function effectively. Gravity adaptation remains a subtle but profound challenge. Long-term exposure to reduced gravity on Mars or potentially stronger gravity on larger exoplanets affects muscle mass, bone density, cardiovascular function, and even reproductive health. Habitats may need to incorporate rotating sections to simulate Earth-like gravity. Or exercise regimes may become mandatory to maintain physical health. Understanding and mitigating the effects of gravity variations is crucial for the success of multi-generational colonies. Radiation protection continues to drive engineering and material science innovations. Mars' thin atmosphere offers little shielding, while Europa and Enceladus benefit from ice layers but still require protection within habitats. Advanced materials that absorb or deflect radiation, combined with strategic habitat design, can create safe zones. Portable radiation shields, smart clothing, or even magnetic field generators may become standard components of daily life, allowing humans to explore safely while minimizing long-term health risks. Psychological resilience is as essential as physical safety. Isolation, confinement, and distance from Earth can lead to stress, anxiety, and social tension. Habitats must include communal spaces, recreation areas, and zones that simulate natural environments to maintain mental health. Virtual reality could supplement physical surroundings, offering immersive experiences of Earth landscapes, cultural events, or interactive social simulations. Maintaining mental well-being is critical not only for individual health, but for community cohesion and overall mission success. Resource utilization drives sustainability. Mining local materials, recycling water and nutrients, and using insight to resources for construction reduce dependency on Earth. Mars offers regolith that can be converted into building materials, while Europa and Enceladus provide water and chemical compounds essential for life support. Exoplanets remain largely unknown, emphasizing the need for scouting missions and robotic assistance to identify viable resources. Efficient resource management ensures long-term survival and enables gradual expansion of colonies. Environmental monitoring is essential for long-term adaptation. Weather patterns, seismic activity, radiation fluctuations, and ice movements must be constantly observed. AI-driven monitoring systems, drones, and autonomous robots can detect hazards, perform maintenance, and respond to emergencies faster than human crews. Early detection allows colonists to prepare, adapt, and survive, transforming potentially life-threatening situations into manageable challenges. Ultimately, the goal is not just survival, it is sustainable, thriving life. Advanced technology, human ingenuity, and careful planning allow colonists to turn hostile environments into habitable worlds. Martian valleys may host lush greenhouses beneath protective domes. Europa's oceans could be explored in pressurized submersibles. And exoplanets may one day support fully enclosed ecosystems tailored to human needs. Each solution not only ensures survival, but creates opportunities for exploration, discovery, and the expansion of human civilization. The interplay between environment and technology fosters continuous innovation. Every challenge: radiation, temperature extremes, limited water, toxic atmospheres, or gravity variations becomes a catalyst for progress. Materials, science, robotics, artificial ecosystems, energy systems, and life support technologies are pushed to new levels. These advancements not only facilitate off-world habitation, but also inspire solutions that benefit Earth, creating a cycle of knowledge and innovation that spans planets. Long-term colonization requires vision, patience, and resilience. Humans must adapt physically, mentally, and socially, learning to coexist with alien landscapes while leveraging technology to overcome environmental challenges. Each successful habitat, each sustainable ecosystem, and each exploration mission lays the groundwork for future expansion. Humanity will not merely visit these worlds. It will transform them into places where life can flourish, where creativity and science merge, and where the dream of interplanetary habitation becomes reality. The universe, with all its extremes, is both a challenge and an invitation. Every frozen moon, distant exoplanet, or rocky desert offers opportunities to test our limits, push the boundaries of knowledge, and create homes in the most unlikely places. Environmental challenges shape human ingenuity, demanding solutions that are as adaptive and resilient as the species themselves. Overcoming these obstacles is the first step toward a future in which humanity is no longer bound to Earth, but thrives among the stars. Terraforming, the process of transforming an alien world into a habitable environment, is one of humanity's most ambitious dreams. It is the bridge between imagining life on another planet and actually creating conditions where humans can thrive without reliance on enclosed habitats or artificial life support systems. While this concept has long been the domain of science fiction, advances in planetary science, engineering, and environmental technology suggest that, in principle, humanity could alter planets like Mars to support life, given sufficient time, resources, and ingenuity. The science of terraforming begins with understanding a planet's existing environment. Mars, for example, offers a compelling target due to its relative proximity and its similarities to Earth, a day length close to 24 hours, polar ice caps, and evidence of past liquid water. However, its atmosphere is thin, composed mostly of carbon dioxide, with low pressure and minimal natural protection from solar radiation. Temperatures swing dramatically from day to night, and dust storms can envelop the planet for weeks at a time. Overcoming these challenges would require deliberate and large-scale interventions to thicken the atmosphere, raise surface temperatures, and generate breathable air. One of the primary strategies for Mars involves increasing the greenhouse effect to warm the planet. Introducing greenhouse gases such as carbon dioxide and methane could trap heat, raising temperatures enough to melt polar ice and release additional gases. This, in turn, could thicken the atmosphere, increasing surface pressure and creating more stable conditions for liquid water. In more advanced stages, reflective mirrors in orbit or solar energy collectors on the surface could be used to focus sunlight and accelerate warming. While these processes may take decades or centuries, the concept demonstrates that a systematic approach to planetary engineering could gradually create an environment capable of supporting plants, microbes, and eventually humans. Terraforming is not limited to Mars. Exoplanets within the habitable zone of their stars may already possess atmospheres, water, and moderate temperatures. In such cases, interventions may focus on refining conditions to suit human needs, such as adjusting atmospheric composition, stabilizing climate patterns, or controlling surface chemistry. Even small modifications could significantly increase habitability, reducing the reliance on protective domes or artificial ecosystems. Advanced terraforming technologies would combine remote sensing, AI-driven modeling, and robotic construction to test and implement these interventions safely and efficiently. A critical aspect of terraforming is the introduction of life itself. Microbes, plants, and other organisms could be strategically deployed to alter atmospheric composition, produce oxygen, and initiate soil formation. Cyanobacteria, for example, are known to release oxygen through photosynthesis and could serve as early colonizers to gradually create a breathable atmosphere. Over time, as the environment stabilizes, more complex organisms could be introduced, creating self-sustaining ecosystems. The concept is similar to what occurred on Earth billions of years ago, when microorganisms transformed the atmosphere, paving the way for complex life. Terraforming, in this sense, is a long-term partnership between humans and biology, using life itself to shape habitability. Energy requirements for terraforming are enormous. Large-scale interventions, such as atmospheric thickening, global heating, or orbital mirrors, demand immense amounts of power. Nuclear reactors, space-based solar arrays, and possibly future fusion technologies could provide the energy necessary to implement these strategies. Autonomous robotics and AI would carry out repetitive and dangerous tasks, ensuring continuous progress without constant human presence. Terraforming is not an instantaneous process. It is a multi-generational endeavor, requiring patience, planning, and careful management of resources. Ethical considerations are also central to terraforming. Altering a planet's environment has profound consequences, especially if life already exists there. Even microbial life could be disrupted or eradicated by human interventions. Balancing the desire for habitability with the responsibility to preserve alien ecosystems is a crucial aspect of future planetary exploration. The debate raises questions about humanity's role in the cosmos, our stewardship of other worlds, and the moral implications of transforming planets for our own use. Technological feasibility is steadily increasing. Advances in material science, energy storage, robotics, and environmental modeling make previously theoretical concepts more plausible. Simulations of planetary environments allow scientists to predict the outcomes of interventions, optimizing strategies to maximize safety and efficiency. Terraforming research also provides practical benefits for Earth, offering insights into climate control, resource management, and ecosystem restoration that may help address global environmental challenges. Terraforming is a process that combines imagination, science, and persistence. It requires long-term vision, often spanning generations, and collaboration across multiple disciplines. The potential rewards a habitable world beyond Earth unprecedented. By carefully studying candidate planets, deploying technology and life strategically, and continuously monitoring progress, humanity could one day transform distant worlds from barren landscapes into thriving habitats. While the timescales and technological hurdles are immense, the science of terraforming is not merely speculative. The principles are grounded in physics, chemistry, biology, and engineering. Each incremental step, from releasing greenhouse gases to deploying microorganisms, from building orbital mirrors to stabilizing atmospheric pressure, brings the dream closer to reality. Terraforming represents the ultimate human challenge, to not just visit another world, but to shape it, nurture it, and make it home. As we delve further into the science of terraforming, the complexity and scale of potential interventions become strikingly apparent. Mars, often considered the prime candidate for human colonization, illustrates both the challenges and opportunities of planetary engineering. One of the first steps in transforming Mars involves thickening its thin atmosphere. With surface pressure less than 1% of Earth's, humans cannot survive without pressurized habitats. By releasing greenhouse gases such as carbon dioxide or engineered super-greenhouse compounds, the Martian atmosphere could gradually warm, potentially liberating frozen CO at the poles. This cascading effect would further increase atmospheric density and surface temperatures, a critical prerequisite for liquid water and the eventual growth of plant life. Orbital mirrors are another ambitious concept. Large reflective surfaces placed in orbit around Mars could focus sunlight onto specific regions, accelerating warming and ice melting. While technically demanding, this method provides targeted control over temperature increases and allows precise modulation of heat input over decades or centuries. Such interventions could produce localized oases where temperatures, pressure, and radiation levels are suitable for initial colonization and experimentation with early ecosystems. Biological terraforming is equally vital. Microbial life can fundamentally alter a planet's environment over time. photosynthetic bacteria, algae, and genetically engineered microorganisms could be deployed to produce oxygen, convert carbon dioxide, and even begin forming primitive soils. Mars' barren surface could gradually become enriched with organic compounds, paving the way for more complex plant life. This staged approach from microbes to hardy plants, and eventually to agricultural crops, reflects an incremental strategy designed to balance planetary modification with human colonization. Timelines. Simulations play a central role in planning these interventions. Advanced computer models allow scientists to predict how introduced gases, orbital mirrors, and biological organisms will interact over time. Variables such as seasonal changes, dust storms, polar ice dynamics, and solar activity can be integrated into predictive models, helping engineers make informed decisions about timing, scale, and risk management. On exoplanets, where direct observation is limited, simulations are even more critical. They help anticipate challenges related to unknown atmospheres, gravity, and orbital mechanics, guiding the design of interventions and robotic exploration missions. Terraforming moons, such as Europa or Enceladus, presents unique challenges. Beneath their icy shells lie vast oceans, shielded from radiation but isolated from sunlight. Techniques for warming ice layers, drilling access shafts, and maintaining habitable zones in subsurface oceans require precision engineering and advanced life support technologies. Energy for such endeavors might come from nuclear reactors or geothermal sources, while autonomous robots and AI systems handle the most dangerous or repetitive tasks. These moons offer opportunities for pocket habitats where humans can live safely beneath protective ice, explore alien oceans, and test technologies applicable to other extreme environments. Ethics remain a core consideration throughout terraforming. Even if microbial life is the only resident on a world, human interventions may irreversibly alter or eliminate it. The question becomes whether humanity has the right to reshape a planet for its own purposes. Some propose creating carefully controlled, isolated regions for human habitation while leaving the rest of the planet untouched. Others suggest a more gradual, experimental approach, monitoring environmental changes and adjusting interventions to minimize ecological disruption. Ethical frameworks will likely evolve alongside technological capabilities, balancing exploration, survival, and planetary stewardship. Long-term sustainability is another cornerstone of terraforming. Beyond creating initial habitable zones, humans must establish systems that maintain and regulate the environment indefinitely. Closed-loop life support systems, efficient energy networks, and self-regulating ecosystems reduce reliance on Earth. Resource extraction, waste recycling, and water management become integral to the ongoing success of a colony. Colonists themselves become stewards of the transformed environment, ensuring that the delicate balance of temperature, atmosphere, and biological activity continues to support life. Terraforming also catalyzes innovation in materials, science, and engineering. Habitats may require radiation-resistant construction, adaptive insulation, and dynamic climate control. Orbital mirrors, solar reflectors, and localized heating technologies push the boundaries of space-based engineering. AI and autonomous robotics are essential for implementing terraforming strategies at scales and in environments beyond human capability. These technologies not only facilitate planetary transformation, but also expand humanity's capacity to operate in extreme environments across the solar system and beyond. Energy management is a persistent challenge in terraforming. Initiatives such as melting polar ice, generating greenhouse gases, or maintaining subsurface habitats demand vast and reliable power sources. Nuclear energy, both fission and potentially fusion, offers consistent output, while solar arrays provide renewable, long-term energy. Energy storage, including advanced batteries and capacitors, ensures continuous operation even during periods of environmental disruption. such as Martian dust storms or the long winters of icy moons. Effective energy strategies underpin all aspects of terraforming, from life support systems to habitat maintenance and exploration missions. Terraforming is not a solitary endeavor. It requires collaboration across disciplines, nations, and generations. Scientists, engineers, biologists, ethicists, and policymakers must work together to design, implement, and monitor interventions. Each step must be carefully evaluated, as planetary systems are delicate and poorly understood compared to Earth. Multi-generational planning is essential, as changes may unfold over decades or centuries. Patience, perseverance, and adaptability define the process, reminding us that transforming worlds is a marathon, not a sprint. Finally, terraforming represents more than engineering. It embodies humanity's desire to explore, adapt, and extend life beyond Earth. Each challenge thin atmospheres, freezing temperatures, radiation, or lack of water becomes an opportunity to innovate, to apply human ingenuity on a planetary scale. Success would mark a milestone in human history, creating worlds where life can flourish, not just survive. Terraforming is the ultimate expression of human curiosity, creativity, and resilience, turning dreams of interplanetary habitation into a tangible, if long-term, reality. As we envision the grand scale of terraforming, the possibilities extend far beyond Mars or nearby moons. Distant exoplanets, some orbiting stars hundreds of light-years away, may already possess the raw materials needed for human life. Yet their atmospheres, temperatures, or gravity levels require adjustment. Advanced terraforming concepts for such worlds involve planetary-scale interventions, from atmospheric engineering to orbital modifications, all guided by sophisticated simulations and AI-driven planning. These projects may span centuries, involving multiple generations of humans, robotic systems, and autonomous monitoring. One of the most ambitious concepts is atmosphere tailoring, where gases are introduced or removed to create a breathable environment. On carbon dioxide-rich planets, oxygen-producing microbes could gradually alter the balance, while super greenhouse compounds regulate surface temperatures. In colder regions, orbital mirrors or space-based energy reflectors could focus sunlight, melting ice caps, or warming oceans. Conversely, on excessively hot planets, reflective aerosols or orbital shading could reduce solar radiation. These interventions must be carefully calibrated. As planetary systems are interdependent, altering one variable may have cascading effects on weather, oceans, and geology. Water management is central to terraforming. Even small bodies of water can stabilize climates and provide essential resources for life. Ice deposits can be melted, rivers redirected, and reservoirs created to support ecosystems. On dry exoplanets, importing volatiles from asteroids or comets has been proposed, delivering water and other essential compounds to initiate ecological cycles. These strategies require precise calculations of mass, trajectory, and timing, ensuring that introduced materials achieve their intended effects without unintended consequences. Biological terraforming remains a cornerstone of long-term planetary adaptation. Microbes, algae, and engineered plants can alter atmospheres, produce soil, and contribute to nutrient cycles, introducing life in stages, starting with hardy microorganisms and eventually expanding to more complex species. Ecosystems to establish resilience before human colonists arrive. Genetic engineering may enable organisms to thrive under extreme conditions, such as low pressure, high radiation, or unconventional soil chemistry. In this way, life itself becomes a tool for shaping habitability, creating self-sustaining environments that evolve over centuries. Energy infrastructure is critical for large-scale projects. Space-based solar arrays, fusion reactors, and nuclear power plants provide the energy necessary for orbital mirrors, heating systems, and robotic construction. Autonomous drones and AI-controlled machines can work continuously, performing tasks too hazardous or repetitive for humans. Energy efficiency, storage, and distribution become central to terraforming, ensuring that interventions proceed safely, predictably, and effectively. Without reliable energy, planetary-scale engineering remains impossible. Ethical frameworks evolve as terraforming becomes more feasible. The introduction of life, alteration of atmospheres, and modification of planetary surfaces all carry profound consequences. Questions arise. Do humans have the right to reshape worlds for habitation? Should untouched planets be preserved as cosmic sanctuaries? These considerations shape how and where terraforming efforts are implemented, influencing strategies that balance human needs with respect for potential alien ecosystems. Monitoring, incremental interventions, and reversible techniques become part of responsible planetary stewardship. Simulations and predictive modeling are indispensable. Advanced computer systems can simulate entire planetary systems, incorporating climate, geology, biology, and orbital mechanics. These models allow planners to test interventions before deployment, assessing risks, predicting outcomes, and refining strategies. For exoplanets, where direct observation is limited, simulations guide the selection of targets, the design of interventions, and the development of autonomous systems capable of implementing terraforming protocols without direct human oversight. Long-term colonization strategies are intertwined with terraforming. Early settlements may rely on enclosed habitats and controlled ecosystems, gradually expanding as external conditions become more hospitable. Multi-generational planning ensures continuity with knowledge, resources, and technology passed down to sustain efforts over decades or centuries. Colonists act as both inhabitants and caretakers, maintaining balance in emerging ecosystems while continuing exploration and development. This interplay between human society and planetary transformation is a defining feature of advanced colonization. Terraforming also drives technological and scientific innovation. Materials resistant to radiation, temperature extremes, and chemical hazards are developed. AI systems capable of planetary-scale monitoring and intervention are refined, and autonomous robotics advances to execute complex tasks in hostile environments. These innovations have applications on Earth, improving energy efficiency, environmental management, and sustainable agriculture. The pursuit of terraforming thus becomes a dual benefit, preparing humanity for interstellar habitation while enhancing life on our home planet. Finally, terraforming embodies humanity's enduring drive to explore, adapt, and extend life beyond its cradle. It is not merely a technical challenge, but a philosophical endeavor, reshaping the relationship between humans and the cosmos. Each successful intervention, whether thickening an atmosphere, melting an ice cap, or introducing the first photosynthetic microbes, represents a milestone in this long-term vision. Terraforming turns barren landscapes into potential homes, converts obstacles into opportunities, and allows humans to imprint life and civilization onto previously lifeless worlds. The scale, timeframes, and ambition of terraforming are staggering. Yet the underlying principles are grounded in science. By combining physics, chemistry, biology, and engineering, humanity can gradually transform planets from inhospitable alien worlds into vibrant ecosystems capable of sustaining life. The dream of terraforming is both practical and inspirational, a testament to human curiosity, resilience, and the desire to reach beyond the limits of our home planet. Traveling to other worlds is a dream that has captivated humanity for centuries. Yet the vastness of space makes it a challenge of unprecedented scale. Even within our own solar system, distances are staggering. Mars, often the first target for colonization, lies an average of 225 million kilometers away from Earth, the moons of Jupiter and Saturn. Potential habitats for humans are hundreds of millions to over 1 billion kilometers distant. Exoplanets orbiting distant stars are even more remote, measured in light years. Getting there requires not only advanced propulsion technology, but also careful planning, resource management, and human resilience. The journey begins with understanding the limits of current propulsion methods. Chemical rockets, such as those used for Earth orbit and lunar missions, provide powerful thrust but are inefficient for long-duration interplanetary travel. They require massive fuel loads and provide limited acceleration, making trips to Mars last months and trips to the outer planets last years. For interstellar travel, chemical propulsion is impractical, demanding alternative methods that can achieve much higher velocities and maintain them over extended periods. Ion propulsion, nuclear thermal engines, and solar sails represent promising advances. Ion drives provide continuous low-thrust acceleration, gradually building speed over months or years. Nuclear thermal engines use nuclear reactions to heat propellant, offering higher efficiency and shorter travel times compared to chemical rockets. Solar sails harness the pressure of photons from the sun or lasers, allowing spacecraft to accelerate without fuel, though they require immense sails and precise navigation. Each method carries trade-offs between speed, energy requirements, and payload capacity. But collectively, they expand the possibilities of human travel to distant worlds. Time is a central consideration in space travel. Even with advanced propulsion, missions to Mars take several months, while journeys to Jupiter's moons may last years. For exoplanets, current technology would require tens of thousands of years. Scientists are exploring faster methods, such as fusion propulsion, antimatter engines, and concepts like the light sail pushed by powerful lasers. While these technologies remain largely theoretical today, research continues with the goal of eventually making interstellar travel feasible. Life support during travel is another critical challenge. Spaceships must provide air, water, food, and waste management for weeks, months, or even years. Closed-loop systems recycling every possible resource are essential for long journeys. Advanced hydroponics and microbial bioreactors can supply fresh oxygen and food, while energy-efficient systems maintain temperature, humidity, and pressure. Redundancy is key. Every system must have backups to prevent catastrophic failures. The psychological aspect of confinement is equally important, requiring spaces designed for comfort, recreation, and mental stimulation. Radiation exposure poses a significant hazard during long-duration space travel. Outside Earth's protective magnetosphere, cosmic rays and solar radiation can damage cells and increase cancer risk. Shielding using water, specialized materials, or even magnetic fields can mitigate exposure. Some mission designs place living quarters in the center of spacecraft, surrounded by fuel or water tanks that double as protective barriers. Continuous monitoring and protective protocols ensure astronauts remain as safe as possible during their voyage. Communication over vast distances also presents challenges. Signals travel at the speed of light, meaning that even messages to Mars take several minutes, and messages to distant exoplanets could take years. Autonomous decision-making becomes essential, as real-time communication with Earth may be impossible. Artificial intelligence, advanced robotics, and pre-programmed protocols allow spacecraft and colonies to respond to unexpected situations without immediate human guidance from Earth. Preparing for arrival is as important as the journey itself. Spacecraft must be designed for entry, descent, and landing on the target world. Mars' thin atmosphere, icy moons, frozen surfaces, or the unknown terrains of exoplanets all require specialized landing technologies. Parachutes, retrorockets, air braking, and robotic landers may be combined to ensure a safe arrival. Precision navigation, trajectory corrections, and careful timing are critical, as even minor errors can result in catastrophic failure. Human factors extend beyond engineering. Extended time in microgravity affects muscles, bones, and cardiovascular health. Strategies include artificial gravity through rotation, rigorous exercise regimens, and medical monitoring to mitigate these effects. Long journeys also demand strong social cohesion among crew members, mental resilience, and protocols for conflict resolution. These factors ensure that when humans arrive at their destination, they are physically, mentally, and socially prepared to begin colonization and exploration. Ultimately, getting to another world is a monumental challenge, but each step forward, from chemical rockets to advanced propulsion, from life support systems to radiation, shielding brings humanity closer to becoming an interplanetary species. The journey itself is an exploration, a laboratory for innovation, and a test of human ingenuity. Traveling through space stretches the boundaries of what is possible, preparing humans to thrive not just on the other side of the solar system, but eventually among the stars themselves. Long-duration space travel introduces unique challenges that extend far beyond propulsion and navigation. A journey to Mars may last 6 to 9 months, depending on orbital alignment, while trips to Jupiter's moons or the outer planets can take years. For exoplanets, travel times under current technology stretch into tens of thousands of years. These durations necessitate robust life support systems, sustainable food production, and strategies to maintain mental and physical health over prolonged periods. Food production during extended missions is critical. Prepackaged rations are insufficient for multi-year voyages, so spacecraft must incorporate hydroponic gardens, algal bioreactors, and possibly lab-grown proteins to provide essential nutrition. Recycling of water, carbon dioxide, and organic waste forms a closed-loop system, reducing dependence on supplies from Earth. Additionally, rotating crops and microbial cultures can maintain soil fertility and air quality, creating a self-sustaining ecosystem inside the spacecraft. Radiation exposure becomes more pronounced the further from Earth's protective magnetic field. Cosmic rays and solar particle events pose serious health risks, including cancer, neurological damage, and genetic mutations. Shielding strategies range from passive protection, such as water or regolith walls, to active measures like magnetic or plasma fields. Crew members may also take shelter in storm-resistant modules during solar flares. Continuous monitoring ensures early warning and intervention, allowing the crew to mitigate risks while continuing the journey. Artificial gravity is another consideration. Extended exposure to microgravity causes muscle atrophy, bone density loss, and cardiovascular changes. Solutions include rotating sections of the spacecraft to generate centrifugal force, providing exercise equipment designed for microgravity, and medical interventions to monitor and counteract physiological decline. These measures help maintain crew health, ensuring they arrive at their destination capable of performing complex tasks and starting a colony. Propulsion innovations play a pivotal role in reducing travel times. Nuclear thermal engines, capable of producing high thrust and efficiency, can have the journey to Mars compared to chemical rockets. Ion drives provide continuous low-thrust acceleration, gradually increasing speed over months or years, making them ideal for cargo missions or robotic scouts. For interstellar targets, concepts like laser-pushed light sails or fusion propulsion may become feasible, allowing spacecraft to approach a significant fraction of the speed of light. These technologies expand the range of human exploration and reduce exposure to the hazards of long-duration travel. Navigation and trajectory planning require precise calculations. Spacecraft must account for gravitational influences of planets, moons, and the Sun, as well as potential hazards such as micrometeoroids and debris. Automated systems constantly adjust course, making minor corrections to ensure accurate arrival. For distant exoplanets, mission planning may involve decades of predictive modeling, with contingencies for equipment failure, energy shortages, or unexpected environmental conditions. Successful navigation is critical not only for reaching the destination, but for ensuring crew safety throughout the voyage. Psychological well-being is as crucial as physical survival. Extended confinement, isolation from Earth, and the vast emptiness of space can induce stress, anxiety, and social tension. Habitats must include communal areas, private quarters, recreation zones, and immersive virtual environments to support mental health. Social cohesion among crew members is maintained through structured routines, conflict resolution protocols, and opportunities for creative or scientific engagement. Maintaining morale ensures that crews remain motivated, resilient, and capable of problem-solving in unforeseen circumstances. Autonomous systems and artificial intelligence are indispensable for managing the complexities of space travel. AI can monitor life support systems, predict equipment failures, and manage energy distribution. Robotics handle repetitive, dangerous, or precision tasks, from navigation corrections to maintenance of external structures. On distant missions, AI becomes essential, as real-time communication with Earth may be impossible. Decisions must be made locally, with spacecraft and crew relying on autonomous systems for guidance and problem-solving. Arrival procedures are meticulously planned. For Mars, descent requires precision timing, as the thin atmosphere limits parachute efficiency, necessitating retro-rockets or hybrid landing systems. Icy moons require landing on unstable surfaces or thick ice, demanding specialized techniques and real-time adjustments. Exoplanets present unknown terrains, requiring reconnaissance by robotic probes before human arrival. Safe landing is not merely a technical challenge. It represents the transition from a controlled spacecraft environment to an alien world, where colonists must immediately begin establishing habitats and assessing local conditions. Long-duration travel also includes contingency planning for emergencies. Equipment failures, medical crises, or unforeseen environmental hazards must be anticipated. Redundant systems, emergency shelters, medical supplies, and backup power sources provide resilience. Crew training emphasizes adaptability, problem-solving, and cross-disciplinary skills, ensuring that astronauts can respond effectively to challenges without immediate support from Earth. These preparations make long interplanetary journeys viable, even under the most extreme conditions. Ultimately, getting to another world is an exercise in human ingenuity, persistence, and collaboration. It is not simply a technical challenge, but a test of endurance, resourcefulness, and adaptability. Each voyage, whether to Mars, the moons of Jupiter and Saturn, or a distant exoplanet, pushes the boundaries of technology, biology, and human experience. The journey itself becomes a laboratory, preparing humanity not only to survive, but to thrive beyond Earth. Beyond Mars and the moons of our solar system, the concept of reaching exoplanets introduces challenges that push technology, human endurance, and imagination to their limits. Interstellar travel is currently beyond our practical capabilities, but scientific speculation provides a roadmap for how it might one day be achieved. Concepts such as fusion, propulsion, antimatter engines, and light sails propelled by high-powered lasers offer the theoretical potential to reach a fraction of light speed. These methods would allow missions to nearby star systems within decades or centuries rather than millennia, opening the door to humanity's first true interstellar voyages. Exoplanet missions would begin long before humans board a spacecraft. Robotic probes would scout the environment, mapping terrain, analyzing atmospheres, and identifying hazards. Advanced sensors could detect signs of water, assess chemical composition, and even search for biosignatures. The data collected would inform ship design, life support requirements, and landing strategies, ensuring that colonists face a known set of challenges rather than an entirely unknown world. In this way, unmanned exploration becomes the foundation of future human expansion across the stars. Energy management for interstellar travel is unprecedented in scale. Fusion or antimatter engines demand immense fuel sources, precise handling, and sophisticated containment systems. Energy efficiency is critical, as every joule conserved can accelerate the journey or support life support systems. Spacecraft would likely carry redundant power sources, including solar arrays, nuclear reactors, and energy storage systems, ensuring continuous operation even in unforeseen circumstances. Autonomous systems monitor energy consumption, adjusting propulsion, heating, and life support to optimize efficiency over decades-long journeys. Long-term sustainability remains a core challenge. Life support for interstellar voyages requires fully closed-loop systems capable of recycling air, water, and food indefinitely. Hydroponics, algae bioreactors, and advanced microbial systems maintain oxygen levels, remove carbon dioxide, and produce nutrition. Genetic engineering may optimize crops and microorganisms to thrive under variable gravity, radiation, and atmospheric conditions. Crew training focuses not only on scientific and engineering skills, but also on maintaining social cohesion, mental health, and adaptability for unforeseen events. Artificial intelligence and robotics are indispensable companions. On voyages where communication with Earth may be delayed by years, autonomous systems perform critical monitoring, maintenance, and problem-solving. Robotics handle construction, repairs, and exploration, allowing humans to focus on strategic decision-making, scientific research, and personal well-being. AI-driven predictive modeling continually adjusts trajectories, environmental controls, and energy allocation, ensuring that spacecraft remain on course and systems function optimally throughout the journey. Landing and establishing initial habitats on exoplanets require unparalleled precision and preparation. Even after decades-long travel, arrival is not a guarantee of success. Atmospheric entry, surface composition, gravity, and local weather all present potential hazards. Strategies include deploying prefabricated habitats, automated construction robots, and modular life support systems that can quickly establish a livable environment. Initial colonists act as both explorers and engineers, assessing conditions, expanding infrastructure, and gradually transitioning the planet toward long-term habitability. The psychological dimension of interstellar travel cannot be overstated. Crews must endure isolation, confinement, and the vast emptiness of space for years or decades. Mental health strategies include private quarters, communal spaces, virtual reality environments, and structured routines. Continuous learning, research, and creative expression provide purpose and engagement, reducing stress and sustaining motivation. Social cohesion, conflict resolution protocols, and leadership structures ensure that even in extreme conditions, the human team can operate effectively and maintain morale. Terraforming and colonization become intertwined with travel. On arriving at a distant world, initial habitats may be enclosed or semi-enclosed, with controlled climates and artificial ecosystems. Over time, terraforming initiatives introducing microbial life, modifying atmospheric composition, or regulating temperature can expand habitable zones. Colonists gradually transition from dependence on spacecraft to reliance on the planet itself, creating self-sustaining ecosystems capable of supporting larger populations. The interplay between travel, survival, and environmental transformation illustrates the full scope of humanity's interstellar ambitions. Ethical considerations expand in scale with interstellar travel. Decisions regarding the introduction of life, alteration of environments, and interactions with potential extraterrestrial ecosystems carry profound implications. Even microbial life requires careful assessment before human intervention. Long-term stewardship, monitoring, and ethical frameworks ensure that humanity expands responsibly, balancing the imperative for survival and growth with respect for alien worlds. These considerations shape the design of missions, the selection of target planets, and the strategies for colonization and terraforming. Ultimately, space travel, whether to Mars, the moons of our solar system, or distant exoplanets, is a test of human ingenuity, endurance, and imagination. Each journey expands our understanding of physics, biology, and engineering, pushing the boundaries of what is possible. The challenges are immense, from propulsion and energy management to life support, psychological resilience, and ethical responsibility. Yet every mission, every voyage, brings humanity closer to realizing the dream of living among the stars, transforming distant worlds into new homes, and ensuring the survival of life beyond Earth. Building human colonies on other worlds is the next natural step after mastering space travel. Once humanity arrives on a planet like Mars, the moons of Jupiter, or a distant exoplanet, the focus shifts from simply surviving to creating thriving, self-sustaining communities. Colonization is not merely about erecting structures. It involves designing an environment that supports life, encourages well-being, and allows society to grow in harmony with its new world. Each colony represents both a technological challenge and a profound human experiment. The first stage of colonization often begins with small, modular habitats. These prefabricated units provide essential protection from extreme temperatures, radiation, and atmospheric differences. They are designed to be lightweight for transport, but robust enough to withstand alien weather conditions. Airlocks, pressure regulation, temperature control, and radiation shielding are standard features. Early colonists live within these structures, gradually expanding them as resources, energy, and local knowledge increase. These habitats also serve as laboratories to study the environment, test life support systems, and determine where future expansion is safest and most sustainable. Energy independence is vital. Colonies rely on a combination of solar panels, nuclear reactors, and, in some cases, geothermal energy. Solar energy is abundant on most planets and moons, but variations in sunlight due to rotation, seasonal changes, or atmospheric conditions must be accounted for. Nuclear and geothermal systems provide consistent, reliable energy, crucial for life support systems, heating, and industrial processes. Energy storage through advanced batteries or chemical storage methods ensures that colonies remain operational even during periods of low sunlight or unforeseen disruptions. Water management is another foundational concern. Even small amounts of accessible water are invaluable, serving not only as a resource for drinking and agriculture, but also as a shield against radiation. Ice mining, recycling, and purification technologies allow colonies to maximize available water. Advanced filtration and closed-loop systems reduce consumption and waste, ensuring that every drop is preserved. Water also supports hydroponic and aquaponic farming systems, providing food and maintaining atmospheric balance within habitats. Food production in alien environments is both a technical and social priority. Hydroponics and aeroponics enable crops to grow without soil, using nutrient-rich water solutions and controlled light. Microbial bioreactors provide protein and essential nutrients, complementing plant-based diets. Over time, colonies can expand agricultural operations, incorporating genetically optimized crops adapted to local gravity, radiation, and atmospheric conditions. Food production is not only about survival. It shapes community structure, mental health, and long-term sustainability. Sharing harvests, engaging in cultivation, and participating in food management become integral parts of daily life. Transportation within and between colony sites also presents challenges. Colonies may begin with localized rovers, autonomous vehicles, and small shuttlecraft to transport people, supplies, and resources. As settlements grow, infrastructure such as tunnels, bridges, and energy-efficient transport systems becomes necessary. Efficient movement of materials ensures that expansion is feasible, supporting construction, agriculture, scientific research, and emergency response. Transportation systems are designed to minimize energy use while maximizing safety and reliability, reflecting the constraints of living far from Earth. Building colonies requires more than physical structures. It requires social infrastructure. Communities need governance, healthcare, education, and recreational spaces. Governance systems are designed to balance efficiency, safety, and fairness, while healthcare addresses both common ailments and conditions unique to low gravity, radiation exposure, or confined habitats. Education ensures that knowledge is preserved, expanded, and adapted for the unique circumstances of the colony. Recreation, culture, and social interaction maintain mental health and reinforce cohesion among settlers, preventing isolation and fostering resilience. Adaptability is key to survival. Alien environments are unpredictable, and colonies must be designed to evolve with changing conditions. Habitats are modular and scalable, allowing for expansion or reconfiguration. Life support systems include redundancies and flexibility, enabling rapid response to failures or environmental changes. Colonists are trained in multiple skills, from engineering and medicine to agriculture and robotics, ensuring that the community can respond effectively to crises. Adaptability is as much a cultural trait as a technical one, embedded in training, social norms, and colony planning. Scientific research is central to colony development. Each settlement acts as both a home and a laboratory, studying geology, atmospheres, biology, and potential terraforming opportunities. Understanding local resources, weather patterns, and geological stability informs the expansion of habitats and infrastructure. Research also focuses on improving life support technologies, optimizing energy use, and testing new agricultural or ecological strategies. By integrating science into daily life, colonies become hubs of innovation and experimentation, pushing humanity's knowledge forward while ensuring survival. Ethical considerations guide the growth of colonies. Human settlement inevitably alters the local environment, and decisions must balance human needs with planetary stewardship. This includes minimizing contamination, preserving pristine areas, and responsibly managing resources. Colonists act as guardians as well as inhabitants, responsible for the health of both their community and the world they inhabit. Ethical planning also encompasses social equity, ensuring that every member of the colony has access to resources, participation in governance, and protection from harm. Ultimately, building human colonies is a profound combination of engineering, biology, sociology, and philosophy. It transforms the dream of living beyond Earth into a tangible reality, creating spaces where humans can survive, thrive, and evolve. Each colony is a microcosm of human ingenuity, resilience, and adaptability, a testament to our desire not merely to explore, but to inhabit, shape, and flourish among the stars. As colonies expand, the challenge shifts from small, modular habitats to larger, integrated settlements capable of supporting hundreds or thousands of inhabitants. Advanced construction technologies become essential. 3D printing with in-situ materials using regolith ice or local minerals allows structures to be built efficiently without relying solely on supplies from robotic construction teams work alongside human settlers, performing repetitive or hazardous tasks and enabling rapid expansion. Domed cities, subterranean networks, and layered habitats maximize space, protection, and environmental control. Energy infrastructure must scale accordingly. Small solar panels and nuclear units are insufficient for larger settlements, so colonies rely on microgrids combining multiple energy sources. Geothermal plants, fusion reactors, and large-scale solar arrays provide consistent, high-capacity power. Smart energy management systems balance supply and demand, redirecting power where needed for life support, agriculture, industrial processes, and research facilities. Redundancy ensures resilience, minimizing the risk of catastrophic failure in isolated environments. Water and air systems must also expand. Advanced recycling, desalination of ice deposits, and atmospheric processing maintain sustainable supplies. Water is distributed across the colony for drinking, agriculture, and shielding, while oxygen levels are monitored and balanced with carbon dioxide scrubbing systems. Maintaining a healthy atmosphere in larger settlements requires careful modeling, continuous monitoring, and rapid response to any anomalies. Failures in these systems can be life-threatening, emphasizing the importance of robust design and preventative maintenance. Food production scales with population. Large hydroponic farms, vertical gardens, and algae reactors provide diverse and nutritious diets. Agricultural cycles are carefully planned to ensure consistent output, with genetic modifications and selective breeding optimizing crops for alien conditions. Livestock may eventually be introduced in controlled environments, contributing protein and organic matter to soil or nutrient systems. Food security is central to both survival and morale, as shared meals and participation in cultivation reinforce social cohesion. Transportation within large colonies becomes a complex challenge. Efficient movement of people, goods, and resources is crucial. Autonomous vehicles, transport tunnels, and maglev systems reduce energy use and increase safety. Cargo delivery networks connect industrial areas, research centers, and residential zones. Internal transport infrastructure allows colonies to expand without compromising efficiency, ensuring that growth remains organized and sustainable. Social and cultural structures grow alongside physical infrastructure. Governance evolves to include representative councils, decision-making protocols, and legal frameworks adapted to the alien environment. Education systems integrate knowledge of Earth-based science with local ecological and geological studies. Healthcare systems address both common and environment-specific medical challenges. From low-gravity muscle degradation to radiation-induced illnesses, recreational and cultural spaces provide essential mental health support, fostering creativity, expression, and community identity. Adaptability remains central to long-term survival. Colonies must anticipate natural hazards, technical failures, and social challenges. Flexible architecture, modular life support systems, and adaptable urban planning enable rapid response to crises. Colonists are trained as multidisciplinary experts, capable of addressing engineering, medical, agricultural, and social challenges. Autonomous monitoring systems, predictive modeling, and contingency protocols provide additional safety, allowing communities to thrive even in unpredictable conditions. Scientific research continues as a core function of the colony. Long-term studies of planetary geology, atmospheres, and potential for terraforming guide expansion strategies. Research into resource extraction, sustainable energy, and closed-loop ecological systems improves colony self-sufficiency. Colonists contribute to global knowledge, reporting findings to Earth or sharing data with other colonies. By integrating science into daily life, settlements become centers of innovation and discovery, accelerating technological advancement while ensuring survival. Colonies also prepare for expansion beyond their initial site. Outposts are established to explore nearby regions, mine resources, or serve as forward bases for terraforming projects. Transportation networks connect these outposts to the main settlement, facilitating trade, communication, and emergency support. These satellite communities extend the reach of human civilization, forming interconnected networks that eventually span entire planetary surfaces. Ethical and environmental stewardship guide expansion. Human activities are designed to minimize contamination of alien environments, preserve potential native life, and sustainably manage resources. Colonists are both inhabitants and guardians, balancing growth with responsibility. Social equity is emphasized, ensuring that all members of the colony have access to resources, education, and participation in governance. Ethics and sustainability are embedded in daily operations, shaping culture and long-term planning. The first long-duration human societies in space set precedents for future generations. They provide insight into governance, resource management, social cohesion, and adaptation under extreme conditions. Lessons learned in these early colonies inform the design of larger settlements, interplanetary trade networks, and eventually interstellar expansion. Each colony is both a home and a blueprint, illustrating the possibilities and challenges of human life beyond Earth. Ultimately, building large-scale colonies transforms humanity from a planetary species into a spacefaring civilization. It demonstrates our capacity for adaptation, innovation, and cooperation in alien environments. From small habitats to thriving cities, each stage reflects the interplay between technology, ecology, society, and ethics. Colonies are more than survival mechanisms. They are the foundations for human culture, knowledge, and civilization among the stars. As colonies stabilize, long-term planning becomes critical. Advanced technologies allow for the creation of self-sufficient communities capable of sustaining life for generations. Energy production scales up with fusion reactors, orbital solar mirrors, and geothermal plants, providing abundant power for expanding infrastructure. Water extraction and recycling systems are optimized, integrating ice mining, atmospheric processing, and closed-loop filtration to support growing populations. Each technological advancement reinforces independence from Earth, making colonies resilient to supply disruptions or emergencies. Housing and urban planning evolve to accommodate population growth. Multi-level habitats, domed cities, and underground settlements provide protection against harsh planetary conditions while maximizing usable space. Urban layouts incorporate agricultural zones, research facilities, industrial areas, and recreational spaces, balancing functionality with quality of life. Transportation networks, autonomous vehicles, tunnels, and energy-efficient transit systems ensure mobility across sprawling settlements, connecting essential services and fostering community cohesion. Food systems continue to expand with vertical farms, hydroponics, aquaponics, and laboratory-grown proteins. Genetic engineering enhances crop resilience to local conditions, while integrated ecosystems recycle nutrients and support biodiversity within controlled habitats. Food security becomes a cornerstone of societal stability, supporting mental well-being, social engagement, and the physical health of colonists. Community participation in agriculture strengthens social bonds and fosters a shared sense of purpose. Education and healthcare systems evolve alongside infrastructure. Schools integrate Earth-based knowledge with local environmental studies, equipping younger generations with skills to manage complex ecosystems, advanced technology, and community governance. Healthcare addresses traditional medical challenges alongside environment-specific issues, such as radiation exposure, low-gravity effects, and psychological stress from isolation. Continuous training ensures that all residents can contribute to problem-solving, maintaining both safety and adaptability within the colony. Governance systems develop to manage increasing complexity. Representative councils, digital voting, and automated monitoring help balance fairness, efficiency, and safety. Ethical frameworks guide resource allocation, environmental stewardship, and conflict resolution. Social norms emphasize cooperation, adaptability, and long-term planning. Governance is not merely administrative. It is cultural, shaping the values, behaviors, and priorities of colonists in a new world. Scientific research becomes an integral aspect of daily life. Colonies are laboratories for studying planetary geology, atmospheric dynamics, resource management, and potential terraforming methods. Research informs expansion strategies, energy utilization, and life support optimization. Colonists contribute to global knowledge, transmitting data back to Earth or sharing findings with other colonies. This integration of science ensures that human settlements are not only sustainable, but also centers of innovation and discovery. Expansion strategies focus on creating interconnected networks of settlements. Satellite outposts, mining stations, and agricultural hubs are linked through efficient transport and communication systems. These networks allow resources, personnel, and knowledge to flow between settlements, reducing isolation and enhancing resilience. As colonies grow, they form the foundations of larger planetary civilizations, with regional planning balancing local autonomy with overall coordination. Cultural development is central to long-term colonization. Art, music, literature, and communal traditions emerge, fostering identity and social cohesion. Celebrations, rituals, and shared experiences reinforce morale, mitigate stress, and cultivate a sense of belonging. Cultural adaptation merges Earth's traditions with new planetary realities, creating unique societies that reflect both human heritage and the distinct conditions of their environment. Ethical and environmental considerations guide growth. Colonists act as stewards, minimizing contamination, preserving pristine regions, and managing resources sustainably. Decisions balance human needs with planetary integrity, ensuring that development does not irreversibly harm potential native life or ecosystems. Social equity ensures access to resources, participation in governance, and protection for all members, reinforcing a sense of fairness and collective responsibility. Ultimately, building human colonies transforms humanity into a multiplanetary species. Colonies evolve from small protective habitats into thriving, self-sustaining societies. They serve as models of adaptability, innovation, and resilience, demonstrating the capacity to survive and flourish in environments far removed from Earth. Each colony represents a fusion of technology, ecology, governance, culture, and ethics, offering a blueprint for future expansion throughout the solar system and beyond. Through careful planning, scientific innovation, and human determination, colonies become more than places of survival. They are centers of growth, learning, and civilization. They embody humanity's ambition to inhabit new worlds, not just as explorers, but as settlers, shaping societies, culture, and environments across the stars. As each colony grows, it brings humanity closer to realizing a vision of a future where life thrives among planets, moons, and distant exoplanets, ensuring the continuity and expansion of human civilization. Life beyond Earth represents a profound shift in human experience. Every day in an alien environment challenges our assumptions, routines, and expectations. From waking up in low gravity to interacting with habitats that blend technology and ecology, daily life is a continuous negotiation between human needs and the realities of an unfamiliar world. These routines are designed to maintain physical health, psychological well-being, and social cohesion, creating a rhythm that allows colonists to thrive. Morning routines often begin with personal hygiene in compact, efficient spaces. Water is recycled meticulously, and even a brief shower requires careful conservation. Air pressure, temperature, and humidity are monitored and adjusted to provide comfort within enclosed habitats. Lighting simulates natural Earth cycles, helping regulate circadian rhythms and mental health. These small details, often taken for granted on Earth, become essential components of daily life, grounding colonists in familiar patterns while accommodating alien conditions. Exercise is not optional, it is critical. Low-gravity or microgravity environments accelerate muscle atrophy and bone density loss. Colonists follow rigorous daily regimens using specialized equipment, resistance devices, and simulated gravity zones. Physical activity maintains strength, balance, and cardiovascular health, ensuring that individuals can perform essential tasks, respond to emergencies, and explore their surroundings. Exercise also serves as a social activity, fostering camaraderie and morale within the colony. Food preparation and meals take on new significance. Hydroponic and laboratory-grown produce is harvested, processed, and consumed in carefully managed portions. Shared meals strengthen social bonds and provide opportunities for collaboration, discussion, and cultural expression. Meal planning incorporates nutritional balance, local crop cycles, and resource efficiency. Food is both sustenance and a medium for community, reinforcing a sense of normalcy and connection to life on Earth. Workdays are structured to balance exploration, maintenance, research, and community needs. Colonists rotate through tasks such as habitat maintenance, scientific experiments, resource extraction, and educational duties. Autonomous systems and robotics assist with repetitive or hazardous tasks, allowing humans to focus on decision-making, creativity, and problem-solving. Flexible scheduling accommodates individual rhythms, ensuring that work is sustainable and mentally engaging over long durations. Leisure and recreation are essential components of daily life. Colonists engage in creative activities, games, and social events to reduce stress and maintain morale. Virtual reality and augmented reality provide immersive experiences, simulating Earth landscapes or fantastical environments. Physical spaces, gardens, communal lounges, exercise areas encourage movement, socialization, and relaxation. These routines support psychological health, preventing isolation and promoting community cohesion. Education and skill development continue throughout daily life. Children and adults alike participate in ongoing learning, integrating Earth-based knowledge with practical skills needed for survival and expansion. Training covers engineering, medicine, agriculture, robotics, and governance. Education ensures that every member of the colony can contribute to problem-solving and long-term sustainability, preparing the next generation to inherit and expand the settlement. Healthcare routines are integrated into daily schedules. Monitoring systems track vital signs, radiation exposure, and environmental conditions. Preventative care, physical therapy, and mental health support are routine, ensuring that small issues are addressed before they become critical. Specialized medical protocols accommodate low gravity, radiation, and confined living spaces, reflecting the unique challenges of alien environments. Regular check-ins create a culture of wellness and vigilance, fostering a community that is both healthy and resilient. Social interaction is carefully nurtured. In small, isolated communities, relationships are essential for stability and morale. Colonists practice empathy, communication, and conflict resolution, maintaining cohesion under prolonged stress. Group activities, collaborative projects, and shared responsibilities reinforce bonds and foster a collective identity. Social structures evolve organically, blending Earth traditions with new cultural practices adapted to alien conditions. Exploration and engagement with the surrounding environment punctuate daily life. Even in established colonies, venturing outside the habitat provides scientific insight, resource opportunities, and psychological benefits. Rovers, exosuits, and exploration drones extend human reach, allowing settlers to study terrain, collect samples, and monitor environmental changes. Interaction with the external world fosters a sense of purpose, curiosity, and connection, linking colonists to the broader planetary ecosystem. Ultimately, life beyond Earth is a delicate balance between adaptation and preservation. Colonists navigate the tension between maintaining human traditions and embracing the alien environment. Daily routines, from personal care to exploration, integrate survival, community, and curiosity. By establishing consistent patterns, supporting well-being, and fostering engagement, settlers transform extraordinary conditions into sustainable, meaningful lives. Advanced technologies shape much of daily life in extraterrestrial colonies. Automated systems monitor habitats continuously, adjusting temperature, humidity, oxygen levels, and energy use. AI-assisted assistants help schedule tasks, manage resources, and provide guidance on technical or environmental challenges. Smart interfaces allow colonists to control habitats efficiently, freeing them to focus on scientific research, creative projects, and social interaction. These systems are crucial for reducing stress, preventing errors, and maintaining both individual and community well-being. Psychological resilience is central to long-term survival. Living in confined spaces, isolated from Earth, and exposed to alien environments can create stress, anxiety, and a sense of detachment. Colonists engage in structured mental health practices, including meditation, virtual therapy, group discussions, and creative outlets. Community rituals, celebrations, and shared accomplishments foster emotional stability and a sense of belonging. The integration of mental health strategies into daily routines ensures that stress does not accumulate. Maintaining morale and overall health over extended periods. Education and cultural development remain active parts of daily routines. Beyond basic schooling, lifelong learning is encouraged. Colonists study planetary geology, atmospheric chemistry, ecological management, and the history of human space exploration. Cultural exchange programs, storytelling, and artistic expression preserve Earth traditions while fostering new cultural practices unique to each colony. Art, music, and literature provide both emotional support and intellectual stimulation, reinforcing identity and community cohesion. Exploration routines are woven into everyday life. Even in established colonies, excursions outside habitats are common for research, resource collection, or environmental monitoring. Colonists use specialized suits, rovers, and drones to safely navigate diverse terrains. Regular exploration fosters curiosity, develops practical skills, and strengthens community bonds. It also serves as a reminder of humanity's ongoing connection to the broader universe, inspiring both awe and purpose in daily life. Community dynamics evolve naturally over time. Colonists form structured social systems, including governance councils, work rotations, and cultural committees. Responsibilities are distributed to balance efficiency, fairness, and individual satisfaction. Community meetings, collaborative projects, and conflict resolution protocols ensure that everyone has a voice and that tensions are managed constructively. Strong social cohesion enhances safety, productivity, and overall satisfaction, enabling the community to withstand challenges inherent to alien environments. Daily, life integrates environmental stewardship. Colonists maintain a constant awareness of their impact on the local ecosystem, even in initially barren or resource-limited worlds. Waste is minimized, recycling is continuous, and energy use is optimized. Terraforming projects or ecological modifications are approached carefully, guided by both scientific evidence and ethical considerations. These practices create a culture of responsibility and mindfulness, ensuring that humanity expands sustainably beyond Earth. Healthcare routines are sophisticated and proactive. Continuous monitoring of physical and mental health, combined with automated diagnostic systems, allows for early detection of potential issues. Preventative care includes exercise, nutrition management, sleep regulation, and stress reduction. Specialized treatments address the effects of low gravity, radiation exposure, and confined living conditions. Medical protocols are integrated into daily schedules, ensuring that both individuals and the community remain healthy and capable of responding to emergencies. Recreational activities adapt to unique planetary conditions. Zero or low gravity environments create opportunities for innovative sports, artistic performance, and physical training. Virtual and augmented reality technologies allow colonists to experience Earth landscapes or fantastical simulations, providing relaxation, entertainment, and creative stimulation. Recreation is carefully balanced with work and research, maintaining psychological well-being and social cohesion while preventing burnout. Food and nutrition remain central to daily life. Meal preparation is an interactive and communal activity, reinforcing social bonds and maintaining cultural continuity. Nutritionally balanced diets are produced through hydroponics, aquaponics, and laboratory-grown proteins, supplemented with locally sourced materials where available. Food systems are integrated with energy and water management, forming a closed-loop ecosystem that supports both health and sustainability. Participation in cultivation, cooking, and food distribution strengthens community engagement and creates a shared sense of accomplishment. Ultimately, life beyond Earth is a continuous interplay of technology, human adaptability, and social organization. Every aspect of daily experience, from personal hygiene to exploration, recreation, education, and governance, is carefully designed to maintain balance, resilience, and meaning. Colonists learn to thrive in extraordinary circumstances, transforming alien environments into places of safety, productivity, and fulfillment. By integrating advanced systems, psychological support, cultural development, and environmental stewardship into daily routines, human settlements become sustainable, resilient, and inspiring examples of life among the stars. As colonies mature, social organization becomes increasingly sophisticated. Communities develop governance structures that balance efficiency, fairness, and individual freedoms. Representative councils, automated decision support systems, and participatory forums ensure that every member has a voice. Leadership rotates periodically, emphasizing responsibility and collaboration. Decision-making frameworks integrate ethical considerations, resource management, and long-term planning, providing stability in environments where unpredictability is the norm. Daily routines are increasingly guided by predictive analytics and smart systems. AI monitors energy consumption, environmental conditions, and resource usage, optimizing workflows and preventing crises before they arise. Colonists receive alerts and guidance, allowing them to focus on creative problem-solving, research, and social engagement. These systems enable long-term sustainability, ensuring that communities can grow without overtaxing their environment or infrastructure. Psychological adaptation continues to play a central role. Colonists develop resilient strategies for extended isolation, confinement, and distance from Earth. Rituals, cultural celebrations, and shared achievements foster mental stability and cohesion. Structured recreational activities, combined with immersive virtual experiences, provide balance, entertainment, and cognitive stimulation. Continuous social support networks allow individuals to navigate stress, interpersonal conflicts, and the unique pressures of extraterrestrial life. Education evolves to meet the needs of an interplanetary society. Schools and training programs incorporate practical skills for habitat maintenance, scientific exploration, and community leadership. Knowledge of Earth is preserved alongside new expertise developed on the colony, creating a culture of innovation and adaptability. Lifelong learning is encouraged, with colonists constantly improving technical, social, and ecological skills. This ensures that each generation is equipped to manage increasingly complex settlements and contribute to the colony's success. Cultural evolution reflects both continuity and adaptation. Traditions from Earth blend with new practices inspired by the alien environment. Music, art, and storytelling provide emotional enrichment and cultural identity. Community rituals mark important events, scientific milestones, and environmental observations, reinforcing social cohesion and shared purpose. Cultural exchange between colonies encourages diversity, creativity, and the development of interplanetary human identity. Exploration becomes a daily yet integral aspect of life. Colonists venture outside habitats to monitor environmental changes, test new technologies, and collect resources. Rovers, drones, and exosuits facilitate safe and efficient movement across alien terrain. Exploration is both practical and symbolic, fostering curiosity, discovery, and a sense of connection to the broader planetary ecosystem. These activities provide purpose and inspiration, integrating scientific research into everyday life. Sustainable resource management guides daily operations. Colonists maintain closed-loop systems for water, air, and nutrients, minimizing waste and ensuring continuous availability. Agricultural, industrial, and habitat processes are closely monitored and optimized for efficiency. Ethical considerations govern extraction and modification of local environments, preserving opportunities for future colonists and potential native life. Sustainability becomes a cultural value, shaping behavior, decision-making, and long-term planning. Healthcare routines remain deeply integrated into daily life. Continuous monitoring of physical and mental health ensures early detection of potential issues. Preventative care, exercise, nutrition, and stress management maintain overall wellness. Advanced medical technologies combined with trained personnel address environment-specific challenges such as radiation, exposure, low gravity effects, and psychological stress. A proactive approach reduces emergencies and promotes a high quality of life, ensuring that the colony can thrive even under demanding conditions. Community engagement and social cohesion are reinforced. How? Through daily interaction, collaborative projects, communal decision-making, and shared responsibilities create a strong sense of purpose and belonging. Colonists participate in governance, resource management, education, and cultural activities, fostering accountability and mutual support. Social bonds reduce stress, encourage innovation, and help the community navigate challenges collectively, strengthening resilience and adaptability. Ultimately, daily life beyond Earth integrates survival, innovation, and community. Colonists learn to balance routine, creativity, and exploration, transforming alien environments into vibrant, sustainable homes. Every task from maintaining habitats to cultivating food, conducting research, and engaging in social and cultural activities contributes to the long-term success of the settlement. Life beyond Earth is not merely about existing. It is about thriving, adapting, and creating a meaningful, enduring human presence among the stars by embedding technological support, psychological resilience, cultural development, and environmental stewardship into daily life. Colonies achieve sustainability and growth. Human communities adapt, evolve, and flourish in alien environments, demonstrating ingenuity, cooperation, and determination. Every day reinforces the possibility that humanity can not only survive beyond Earth, but also cultivate a rich, rewarding, and dynamic life, paving the way for future generations to expand further into the cosmos. The question of whether other planets could be better than Earth captures the imagination and challenges our understanding of life, environment, and civilization. Earth is home to abundant life, diverse ecosystems, and a stable climate. Yet it also faces limitations: finite resources, natural disasters, climate change, and social challenges. The notion of a planet that could surpass Earth in habitability, beauty, or potential for human flourishing invites both scientific inquiry and philosophical reflection. Astronomers have discovered thousands of exoplanets, planets orbiting stars beyond our Sun, some of which may offer conditions surprisingly favorable for life. Better can be defined in many ways: a planet with abundant water, a temperate climate, lower radiation levels, fertile soil, or a more stable orbit. Some exoplanets orbit stars that provide ideal light and warmth, without the extreme variability seen on Earth. Others may offer unique advantages, such as higher gravity for muscle development, stronger magnetic fields for radiation protection, or less exposure to catastrophic events like asteroid impacts. Life-supporting potential depends on numerous factors: atmosphere composition, temperature range, availability of liquid water, and presence of protective magnetic fields all play roles. Some exoplanets in the habitable zone have been identified as prime candidates, where temperatures allow water to exist in liquid form. These planets may possess rich chemical diversity, which could support either natural ecosystems or human-engineered habitats. Researchers use telescopes, spectroscopic analysis, and computer modeling to estimate these properties. gradually building a map of potentially superior worlds. The idea of a better planet also raises questions about human preferences. What makes Earth desirable goes beyond mere survival. Humans value aesthetic beauty, biodiversity, and cultural familiarity. Some exoplanets may have breathtaking landscapes, towering mountains, or vast oceans, but with alien skies, unfamiliar sunlight, or atmospheric colors that challenge our perception. Would a planet with perfect climate but an alien visual palette feel like home? The interplay between physical habitability and psychological satisfaction becomes central when imagining life on another world. Gravity is another factor in evaluating planetary superiority. Low gravity reduces energy expenditure for movement, but long-term exposure can weaken muscles and bones. High gravity provides resistance training, promoting physical fitness, yet constrain the cardiovascular system and limit mobility. An ideal planet would strike a balance, supporting healthy development while not imposing extreme physical challenges. Earth's gravity is well adapted for humans, but minor variations might be preferable for certain physiological benefits or for specific types of human activity. Radiation protection is equally vital. Earth benefits from a magnetic field and atmosphere that shield life from harmful cosmic rays and solar radiation. Planets lacking these defenses pose long-term health risks, even if they offer other advantages such as abundant water or temperate climates. In this context, a better planet may be one that provides natural shielding, reducing the need for artificial protection and enabling more open, flexible living conditions. Resource availability defines another dimension of planetary desirability. Planets rich in water, minerals, and usable energy sources offer opportunities for sustainable settlement, research, and even industry. Access to raw materials for construction, energy generation, and life support systems reduces dependence on Earth, allowing colonies to flourish independently. Some exoplanets may possess abundant ice deposits, fertile soils, or rare minerals, providing both survival essentials and potential economic opportunities. Stability and predictability also influence perceived superiority. Earth experiences seasons, storms, earthquakes, volcanic eruptions, and climate fluctuations. A more stable planet, one with consistent weather patterns, minimal seismic activity, and predictable orbital dynamics, could allow for safer, more efficient planning of settlements, agriculture, and infrastructure. Stability reduces risk and allows for a smoother integration of human civilization, potentially creating an environment more conducive to long-term growth. However, the concept of better is not absolute. Every planet, no matter how ideal it may seem, presents challenges. Alien ecosystems, unfamiliar chemical environments, and potential hazards could offset perceived advantages. Ethical considerations emerge as well. What if these worlds harbor life, microbial or complex? Would colonizing or modifying them truly be better if it disrupts native organisms? These questions intertwine scientific assessment with moral reflection, highlighting the complexity of evaluating planetary superiority. Ultimately, exploring whether other planets could surpass Earth requires both imagination and rigorous science. Observations, simulations, and theoretical models allow us to envision worlds that may rival or even exceed Earth in specific aspects. Yet human experience, social needs, cultural identity, and ethical considerations shape our understanding of what better truly means. A planet that is physically ideal may not meet emotional or societal expectations, while one that challenges us may still enrich human life in ways Earth cannot. Scientists have identified numerous exoplanets that could theoretically support human life under the right conditions. Some of the most intriguing candidates are located within the habitable zones of their stars, where temperatures allow liquid water to exist. Kepler 4.5b, often called Earth's cousin, is slightly larger than Earth and receives a similar amount of sunlight, suggesting temperate conditions. while much remains unknown about its atmosphere and surface. It serves as a compelling example of the type of world that could rival or even surpass Earth in terms of habitability. Another intriguing candidate is Proxima Centauri b, orbiting the nearest star to our Sun. Although its red dwarf star presents challenges, including increased stellar flares and radiation, technological adaptation could mitigate these risks. Protective domes, underground habitats, or magnetic shielding could allow human life to thrive even under intense stellar activity. Colonists might harness advanced energy collection systems and employ autonomous monitoring to ensure safety and sustainability. TRAPPIST-1e, one of the 7 Earth-sized planets in the TRAPPIST-1 system, offers another compelling scenario. Its size and density are similar to Earth's, suggesting rocky terrain and the potential for water retention, while tidal locking could create extreme temperature variations between the day and night sides. Innovative settlement strategies, such as habitats along the Terminator line where temperatures are moderate, could turn these challenges into opportunities. Engineering solutions could also include orbital mirrors or controlled climate domes to regulate local conditions. Adapting to these alien worlds requires both technological ingenuity and human flexibility. Life support systems must regulate atmosphere, pressure, temperature, and radiation exposure. Closed-loop ecosystems recycle air, water, and nutrients efficiently, allowing colonies to thrive with minimal resupply from Earth. Advanced robotics and AI assist with habitat construction, maintenance, and exploration, reducing human exposure to hazards and enabling settlements to expand faster than manual labor alone would allow. Gravity variations present both opportunities and challenges. Colonists may use artificial gravity chambers or rotating habitats to simulate Earth-like conditions, mitigating muscle atrophy and bone loss in low-gravity environments. In higher gravity settings, adaptive exercise regimens, modified construction techniques, and tailored clothing or exoskeletons could help humans maintain health and mobility. These adaptations demonstrate that even planets initially less hospitable can be transformed into environments suitable for long-term human habitation. Water availability is a critical factor in evaluating better planets. Some worlds may have vast ice deposits or liquid water beneath their surfaces, allowing colonists to extract and purify it for drinking, agriculture, and industrial use. Technologies such as atmospheric water capture, ice mining, and desalination systems could provide reliable water sources. Efficient water management not only sustains life, but also supports energy generation, agriculture, and ecological balance within closed-loop habitats. Atmospheric composition is another determinant. Earth-like atmospheres rich in oxygen and nitrogen are ideal, but many candidate planets have alternative compositions. Habitats may rely on pressurized, oxygenated environments while maintaining minimal leakage into the alien atmosphere. Controlled biospheres, hydroponic farms, and sealed living quarters create livable microenvironments, allowing humans to experience Earth-like air quality even on planets with thin or toxic atmospheres. Temperature regulation is equally essential. While some exoplanets boast average temperatures suitable for life, extreme variations can occur due to axial tilt, orbital eccentricity, or tidal locking. Colonists can mitigate these challenges with insulation, localized heating or cooling systems, reflective surfaces, and climate-controlled domes. By engineering microclimates, humans transform raw planetary conditions into habitats optimized for comfort, productivity, and survival. Solar and stellar energy also influence planetary desirability. Stars that provide stable light and energy output allow for consistent solar power, while extreme variability or intense flares may require energy storage systems, shielding, or alternate power sources. Colonists must design energy grids that are robust, redundant, and adaptable, ensuring continuous access to electricity for life support, communication, and technological systems. Ultimately, The concept of better planets extends beyond mere survival. A superior planet might offer easier access to essential resources, a more stable environment, opportunities for exploration, and potential for aesthetic or recreational enjoyment. Human adaptability, combined with advanced technologies, allows settlers to harness these advantages while mitigating inherent challenges. Even worlds that initially seem less hospitable can be transformed into thriving habitats. Expanding the boundaries of human civilization, ethical and philosophical considerations shape our understanding of these opportunities. Colonizing a new planet involves responsibility toward potential native life, planetary ecosystems, and future generations. Balancing the desire for improved living conditions with the duty to preserve and respect alien environments ensures that humanity's expansion is sustainable, just, and mindful. Evaluating planetary superiority is therefore both a scientific and moral exercise. Integrating technology, biology, culture, and ethics into a unified vision for interplanetary life. Long-term colonization strategies transform the concept of better planets from theory into reality. Once a suitable world is identified, settlers focus on creating sustainable habitats that integrate with local environments while meeting human needs. Modular habitats, capable of expansion and adaptation, provide flexible living and working spaces. These structures are designed to withstand environmental stresses such as temperature fluctuations, radiation, and seismic activity, while supporting agriculture, recreation, research, and social interaction. Ecosystem design becomes a central component of successful colonization. Closed-loop systems replicate Earth-like cycles of water, nutrients, and air, ensuring that resources are continuously recycled. Hydroponic gardens, aquaponic farms, and microbial ecosystems maintain food production and oxygen levels, creating microcosms of Earth within alien landscapes. Careful attention to species selection, nutrient flow, and energy balance ensures resilience against potential disruptions. Fostering ecological stability within the colony, energy management is vital for long-term survival and comfort. Solar, wind, geothermal, and nuclear energy sources are harnessed to maintain life support, lighting, heating, and industrial operations. Storage systems and smart grids optimize usage, balancing supply with demand and protecting against environmental variability. Reliable energy infrastructure allows colonies to expand, develop new habitats, and support scientific research without constant dependence on Earth-based resupply. Missions. Human comfort and satisfaction remain a guiding principle in habitat design. Recreational areas, cultural spaces, and community centers provide opportunities for leisure, socialization, and creative expression. Virtual and augmented reality technologies supplement experiences that cannot be directly replicated in alien environments, offering immersive simulations of Earth's landscapes, natural phenomena, and artistic creations. These elements enhance psychological well-being, strengthen social cohesion, and create a sense of home away from Earth. Adaptation strategies address physiological and psychological challenges. Gravity variations, atmospheric differences, and radiation exposure require continuous monitoring and intervention. Exercise regimens, protective suits, and controlled habitat environments prevent long-term health issues. Mental health programs, including counseling, mindfulness, and recreational activities, help colonists manage stress, isolation, and the psychological impact of alien surroundings. By integrating these measures into daily routines, communities maintain resilience and human performance. Education and training evolve to meet colony-specific needs. Knowledge transfer from Earth is combined with local experimentation and innovation, fostering adaptive problem-solving and scientific progress. Colonists learn to manage habitats, optimize resource use, conduct research, and navigate environmental challenges. Children and adults alike participate in learning programs that prepare them for leadership. technical roles, and community stewardship. Ensuring continuity and growth across generations, cultural development shapes the identity of interplanetary societies. Traditions, celebrations, and artistic expression are adapted to new environments, creating unique cultural narratives. Community rituals, shared festivals, and collaborative projects reinforce social bonds and provide meaning within extraordinary circumstances. These cultural practices balance continuity with innovation, allowing settlers to preserve a sense of heritage while embracing the opportunities and aesthetics of alien worlds. Exploration and expansion are continuous aspects of life. Colonists establish scientific outposts, resource stations, and exploration teams to study surrounding landscapes and identify potential expansion sites. Robotics, drones, and autonomous vehicles assist in surveying hazardous or distant areas, while human teams interpret findings and make decisions. Exploration enhances knowledge, stimulates curiosity, and provides tangible benefits for colony growth, reinforcing a culture of discovery and adaptation. Ultimately, the concept of a better planet integrates physical conditions, technological capacity, human adaptability, and societal design. A world may surpass Earth in certain dimensions: climate stability, resource abundance, or safety, but its true value is realized through human ingenuity, cooperation, and long-term stewardship. Colonists transform raw planetary conditions into habitable, thriving communities, blending science, technology, and culture to create enriched lives beyond Earth. Satisfaction and well-being guide continuous development. By carefully balancing work, leisure, social interaction, and exploration, colonies ensure that life is not merely survivable, but rewarding. Access to natural beauty, opportunities for creativity, shared accomplishments, and effective problem-solving contribute to a sense of purpose and fulfillment. In this sense, better encompasses not only environmental or physical advantages, but also the richness of human experience, social cohesion, and emotional resilience. In conclusion, the search for planets better than Earth is a multidimensional pursuit. Scientific discovery, technological innovation, ecological design, social organization, and cultural adaptation all contribute to evaluating and realizing the potential of extraterrestrial habitats. While Earth remains uniquely suited to human life, other worlds may offer advantages that, when combined with careful planning and human ingenuity, create environments where life can not only continue but flourish. The vision of a superior planet is both a scientific challenge and a source of inspiration, inviting humanity to expand its presence across the cosmos, adapt creatively, and explore the full potential of life beyond Earth. As humanity contemplates life beyond Earth, philosophical and ethical considerations become as important as technological and scientific questions. The prospect of colonizing other planets raises profound questions about our responsibilities, rights, and moral obligations. Can humans ethically alter alien environments to suit our needs? Should we prioritize survival and expansion over the preservation of untouched ecosystems? These questions challenge our deepest assumptions about humanity's role in the universe. One central ethical dilemma involves potential extraterrestrial life. Even microbial organisms, if present, represent independent life forms with intrinsic value. Altering or terraforming a planet without knowledge of native life may result in irreversible harm. Philosophers and scientists debate whether human survival and progress justify such risks, or whether caution and restraint should guide all interplanetary activities. The discussion mirrors historical debates on colonization and resource exploitation on Earth. But with higher stakes, the alien ecosystems we encounter may never recover from human interference. Human identity and cultural continuity also factor into ethical reflection. Colonization may require leaving behind aspects of Earth culture or adapting to alien environments in ways that fundamentally change our daily lives, social structures, and worldviews. philosophical questions emerge about what it means to be human in a radically different environment. Are humans defined by biology, cultural heritage, shared experiences, or a combination of these factors? As we expand into space, these questions become practical as well as existential. Resource allocation presents another ethical challenge. Expanding human civilization to other planets requires energy, materials, and infrastructure. Who decides which planets to prioritize, which technologies to deploy, and how resources are distributed among Earth and off-world populations? Decisions that might seem purely technical are deeply ethical, influencing justice, fairness, and equality on a planetary and interplanetary scale. Ethical frameworks must guide these choices to prevent exploitation, inequity, or harm to future generations. The concept of planetary stewardship becomes central. Humans must balance the desire for exploration and habitation with the responsibility to maintain ecological integrity. Even barren planets or moons may have delicate geophysical or chemical systems that could be disrupted by settlement. Ethical colonization involves minimizing environmental impact, preserving natural features, and considering the long-term sustainability of human and non-human systems alike. Philosophical reflection ensures that actions taken for survival or convenience do not undermine broader moral obligations. Technology introduces new ethical dimensions. Advanced robotics, AI, and autonomous systems can extend human capabilities, but they also raise questions of control, accountability, and unintended consequences. Should AI have authority in decisions that affect planetary ecosystems or human well-being? How do we ensure that automated systems do not prioritize efficiency over ethical considerations? Thoughtful integration of technology requires foresight, transparency, and ongoing philosophical reflection to balance capability with responsibility. Human health and well-being present additional ethical concerns. Life in alien environments exposes humans to risks including radiation, low gravity, psychological stress, and potential pathogens. Ensuring informed consent, equitable distribution of protective technologies, and access to healthcare are not just practical requirements, they are moral imperatives. Colonists must understand risks, participate in decision-making, and have systems in place to safeguard both individuals and communities. Exploration itself carries philosophical significance. By reaching for other worlds, humanity affirms curiosity, creativity, and the drive to understand the universe. Yet exploration also entails responsibility. Each step, excavation, or modification can alter alien environments irreversibly. Ethical reflection asks whether exploration should be limited to observation or whether intervention is justified. Philosophers debate the moral limits of human ambition. Encouraging careful deliberation before action, cultural ethics must evolve alongside technological progress. Colonies will develop new traditions, norms, and social structures that differ from Earth. Ethical frameworks must guide these developments, ensuring respect for individual autonomy, communal well-being, and intercultural understanding between colonies and Earth by considering the philosophical implications of social organization. Communities can cultivate environments that foster harmony, creativity, and resilience in alien settings. Ultimately, philosophical and ethical considerations shape the very vision of human life beyond Earth. Decisions about which planets to settle, how to modify environments, how to interact with potential life, and how to structure societies are inseparable from questions of morality, identity, and purpose. Space colonization is not only a scientific or engineering endeavor, it is a profound moral journey, challenging humanity to act responsibly, creatively, and reflectively on a cosmic scale. As humanity advances toward extraterrestrial habitation, the question of legal and ethical governance becomes increasingly urgent. International space law, currently grounded in treaties such as the Outer Space Treaty of 1967, provides basic frameworks. Space is considered a global commons, and nations cannot claim sovereignty over celestial bodies. Yet these treaties were conceived in an era when space travel was limited. The ethical challenges of full-scale colonization, planetary resource management, habitation rights, and environmental stewardship require updated laws and morally grounded guidelines that extend beyond national or corporate interests. Global collaboration is central to ethical colonization. Unlike Earth, where nations compete for resources and influence, extraterrestrial endeavors demand cooperation for survival, sustainability, and shared knowledge. Ethical frameworks should encourage transparency, equitable resource distribution, and mutual responsibility among nations, corporations, and independent research groups. Failure to adopt cooperative principles could lead to conflict, exploitation, and long-term environmental harm, undermining both the moral and practical goals of space exploration. The principle of intergenerational responsibility is particularly relevant. Decisions made today regarding planetary settlement, resource extraction, and environmental modification will affect countless future generations. Colonists must consider not only immediate survival, but also the long-term consequences of their actions on planetary ecosystems, technological infrastructure, and social cohesion. Philosophical reflection emphasizes that ethical colonization is not just about human convenience, but about the moral duty to preserve options and opportunities for those who will inhabit these worlds after us. Emerging ethical questions also concern artificial intelligence and robotics. As colonies rely increasingly on autonomous systems for resource management, habitat construction, and exploration, moral dilemmas arise. Should machines be granted decision-making authority in situations where human life is at stake? How do we prevent AI from prioritizing efficiency or planetary manipulation over human and environmental well-being? Developing ethical frameworks for AI governance ensures that technology serves humanity without compromising safety, fairness, or ecological integrity. Equity within colonies is another crucial concern. Access to resources, technology, and opportunities must be fair and transparent. Social hierarchies, if left unchecked, could reproduce systemic inequities from Earth, leading to tension and unrest. Ethical considerations demand proactive policies that encourage inclusion, participation, and equal access to healthcare, education, and leadership roles. Colonies must cultivate a culture of shared responsibility, ensuring that no individual or group is disproportionately burdened or excluded from decision-making processes. Environmental ethics extend beyond human survival to the preservation of planetary integrity. Terraforming, resource extraction, and habitat construction can fundamentally alter landscapes and geochemical cycles. Ethical colonization requires weighing human benefits against potential ecological consequences. Strategies such as minimal impact construction, regenerative agriculture, and careful monitoring of environmental changes embody a philosophy of stewardship, respecting the intrinsic value of alien worlds while supporting human habitation. Cultural ethics also intersect with philosophical considerations. Colonists carry Earth traditions, beliefs, and social norms, yet they must adapt these to new environments. Ethical reflection involves balancing continuity with innovation, preserving cultural heritage while embracing the unique demands and opportunities of alien habitats. This process includes acknowledging potential conflicts between Earth-centric values and the realities of life on other planets, fostering dialogue, flexibility, and mutual understanding. In scenarios where alien life is discovered, ethical complexity multiplies. Any detected organisms, no matter how simple, raise moral questions about human interaction. Scientists and settlers must evaluate the consequences of introducing Earth life, altering habitats, or exploiting local resources. Philosophical frameworks encourage restraint, observation, and non-interference whenever possible. emphasizing the ethical responsibility to avoid harm and respect the autonomy of other life forms. Psychological ethics are also vital. Colonists will face isolation, confinement, and unprecedented social pressures. Ensuring mental health, personal autonomy, and community cohesion is both a moral and practical imperative. Policies and cultural norms must promote fairness, inclusion, and support systems that reduce psychological stress. Ethical considerations guide the creation of environments where individuals can thrive emotionally, intellectually, and socially, even under challenging extraterrestrial conditions. Ultimately, philosophical and ethical reflection informs every aspect of space colonization, from technological deployment to governance, environmental stewardship to social cohesion. Humans must act with foresight, responsibility, and moral clarity. Colonization is not merely a technical achievement, but a test of humanity's ethical capacity, our ability to expand, explore, and innovate without sacrificing principles of justice, fairness, and respect for life. By embedding ethics into every stage from planetary selection and resource use to colony governance and ecological management, humanity can ensure that expansion into space is not only feasible but morally sound. The decisions we make today will shape the legacy of human civilization across the cosmos, highlighting the profound responsibility inherent in our pursuit of life beyond Earth. As we look toward the future, the question of human habitation beyond Earth is no longer purely speculative, it is an emerging reality shaped by science, technology, and imagination. From the earliest telescopic observations of distant worlds to today's discoveries of thousands of exoplanets, humanity's fascination with life beyond our planet has evolved into tangible plans for exploration, colonization, and sustainable habitation. The path forward is complex, filled with scientific challenges, technological innovations, and profound philosophical questions. Yet the vision of humans thriving on other planets remains a source of hope and inspiration for generations to come. The journey from Earth to another world requires not only rockets and habitats, but also adaptability and resilience. Each step, from identifying candidate planets to building sustainable communities, demands ingenuity and patience. Scientists and engineers work tirelessly to develop propulsion systems, life support technologies, and habitat designs that can withstand alien environments. Meanwhile, ethical and philosophical frameworks guide decision-making, ensuring that exploration respects both potential extraterrestrial life and the long-term sustainability of human civilization. The integration of technology, morality, and creativity becomes the foundation for a new era of human existence beyond Earth. Looking ahead, potential colonists may inhabit planets with unique landscapes, climates, and ecosystems, worlds that challenge our perceptions of what a home can be. Some may find planets with milder climates than Earth, stable atmospheres, or abundant resources, while others will require extensive terraforming, engineering solutions, or protective habitats to support human life. Regardless of the challenges, the human capacity for adaptation and innovation remains our greatest asset. By combining scientific understanding with practical ingenuity, we can transform distant worlds into thriving homes for human civilization. The future of interplanetary habitation also depends on collaboration. No single nation or organization can undertake the scale of exploration and colonization required. International partnerships, shared knowledge, and coordinated planning will define successful endeavors. Cooperative models for resource management, research, and ethical oversight ensure that humanity's expansion is not driven by competition alone, but by shared responsibility and a collective vision of sustainable life beyond Earth. These collaborations reflect our capacity to balance ambition with prudence, curiosity with care, An innovation with ethics. Human experience on other planets will redefine the concept of daily life. Settlements will be designed not only for survival, but for comfort, well-being, and growth. Closed-loop ecosystems will provide fresh air, clean water, and sustainable food sources, while recreational and cultural spaces nurture psychological health and social cohesion. Life in these habitats will blend the familiarity of Earth with the novelty of alien worlds, encouraging creativity, exploration, and a renewed sense of wonder. Colonists will experience landscapes and phenomena unimaginable on Earth, reshaping their understanding of nature, beauty, and the universe itself. Technology will play a central role in daily life, extending human capabilities and enhancing adaptation. Autonomous systems, robotics, and artificial intelligence will assist with construction, maintenance, and exploration, allowing humans to focus on creativity, learning, and community building. Energy systems will harness solar, geothermal, and nuclear sources, providing reliable power for life support, research, and industry. Advanced communication networks will keep colonies connected to Earth, enabling knowledge exchange, collaboration, and social interaction across vast distances. Despite technological support, human adaptability remains paramount. Physical and psychological resilience will determine success in alien environments. Colonists will need to navigate differences in gravity, atmospheric composition, and radiation exposure, developing routines, exercises, and protective measures to maintain health. Social cohesion, mutual support, and community engagement will be critical, ensuring that individuals thrive not only physically but emotionally and intellectually. The human spirit, curiosity, ingenuity, and the desire for connection will drive exploration and adaptation on every world we inhabit. The philosophical dimension of interplanetary life continues to evolve. Living on other planets challenges our assumptions about what constitutes home, community, and identity. Humans may develop new cultural practices, ethical norms, and artistic expressions unique to their extraterrestrial surroundings. These developments remind us that colonization is not simply a physical endeavor, but a cultural and intellectual journey, reshaping humanity's understanding of itself and its place in the cosmos. Ethical stewardship remains central to the long-term success of human habitation beyond. Earth colonists must balance the desire to adapt alien worlds with respect for potential life forms, ecosystems, and planetary integrity. Decisions about terraforming, resource utilization, and environmental modification carry profound responsibilities. By integrating ethical considerations into every stage of colonization, humanity ensures that exploration does not come at the expense of moral principles or the long-term viability of extraterrestrial habitats. Ultimately, the future of human habitation beyond Earth is a tapestry woven from science, technology, imagination, ethics, and resilience. Each discovery, innovation, and ethical decision brings us closer to a reality where humans thrive across multiple worlds. While challenges remain immense, the vision of interplanetary life inspires generations to push boundaries, embrace creativity, and act with responsibility. It reminds us that exploration is not only about reaching new worlds, but about understanding ourselves, our potential, and our capacity to coexist harmoniously with the universe. As humanity stands on the threshold of interplanetary expansion, the future of life beyond Earth is both exhilarating and uncertain. Scientific advances, technological innovation, and philosophical reflection converge to create possibilities once considered the realm of science fiction. Within decades, humans may inhabit multiple worlds, exploring diverse landscapes, building sustainable habitats, and adapting to environments radically different from our home planet. The trajectory of this journey depends not only on engineering and biology, but also on our imagination, ethics, and capacity for long-term planning. The expansion into space will likely occur incrementally, beginning with orbital habitats and moon bases before progressing to Mars and beyond. Each stage serves as both a learning ground and a test of human adaptability. Orbital stations allow us to refine life support systems, understand microgravity effects on physiology, and develop sustainable agriculture in controlled environments. Lunar colonies offer the first experience with low-gravity surfaces, resource extraction, and remote communication across vast distances. Mars, with its relatively Earth-like day cycle and accessible terrain, represents the first major step toward permanent planetary colonization, challenging humans to create self-sustaining habitats in a harsh but promising environment. Beyond Mars, the search for potentially habitable exoplanets opens new frontiers. The discovery of planets within habitable zones, coupled with advanced propulsion technologies, suggests that interstellar travel may eventually be feasible. Concepts such as nuclear fusion, propulsion, antimatter engines, or light sail systems could allow humans to reach nearby star systems within decades or centuries. While these possibilities remain speculative, research and experimentation continue to push the boundaries of what is technically achievable, transforming dreams of distant colonization into plausible objectives for future generations. The evolution of human society in extraterrestrial environments will redefine civilization itself. Communities on other planets must balance survival needs with social cohesion, mental health, and cultural expression. Innovations in habitat design, including modular, expandable structures, integrated ecological systems, and AI-assisted resource management, will shape daily life. Social norms, governance structures, and ethical frameworks will evolve to meet the unique challenges of alien worlds. These adaptations may result in societies that differ fundamentally from Earth-based communities while maintaining core human values of cooperation, creativity, and exploration. Ethical and philosophical considerations will continue to guide these endeavors. Decisions about planetary stewardship, resource utilization, and interaction with potential extraterrestrial life forms must balance human ambition with responsibility. The principle of do no harm extends beyond Earth, urging careful consideration of ecological impacts, intergenerational responsibility, and moral obligations to sentient life. Colonization is not merely an exercise in survival, it's a test of humanity's ability to act thoughtfully, ethically, and sustainably in the cosmos. Technological innovation will underpin the feasibility of this future. Life support systems, energy infrastructure, communication networks, and autonomous robotics will enable humans to thrive in environments once deemed inhospitable. Advances in biotechnology and materials science may allow adaptation to diverse gravity levels, atmospheric conditions, and radiation exposure. Even artificial intelligence will play a critical role, assisting with decision-making, monitoring ecosystems, and optimizing resource use. The integration of technology with human ingenuity ensures that expansion beyond Earth is not just possible, but sustainable and resilient. Environmental challenges, however, will remain significant. Each planet presents unique hazards, from intense radiation and extreme temperatures to thin or toxic atmospheres, and geological instability. Colonists must employ adaptive strategies, including protective habitats, underground settlements, and engineered ecosystems, to mitigate risks. Understanding planetary geology, climate patterns, and potential hazards will be essential for long-term success, requiring ongoing research and monitoring. Human adaptability, combined with technological solutions, will transform these challenges into opportunities for innovation and discovery. Ultimately, the future of human habitation beyond Earth embodies both opportunity and responsibility. Expansion into space is not simply about survival. It is an invitation to explore, innovate, and redefine what it means to be human. By building sustainable colonies, fostering ethical practices, and embracing cultural and intellectual growth, humanity can create thriving societies across the cosmos. The journey ahead demands courage, creativity, and reflection. But it also promises the fulfillment of a profound dream: life among the stars, enriched by the knowledge, experience, and imagination of generations to come. Looking further ahead, humanity's expansion into the cosmos may give rise to entirely new forms of society. As colonies become self-sustaining, communities will evolve to reflect the unique environmental, technological, and social conditions of their respective planets. Governance structures may shift from centralized, Earth-based models to decentralized, adaptive systems tailored to the needs and challenges of each habitat. Ethical, cultural, and social norms will be influenced by local conditions, resource availability, and interactions with other colonies, leading to diverse civilizations interconnected through communication, trade, and shared knowledge. Interstellar communication and transportation will play a central role in maintaining cohesion among human settlements. Advanced communication networks, potentially leveraging quantum entanglement or laser-based systems, could enable real-time or near-instantaneous exchange of information across vast distances. Transportation technologies will continue to advance, allowing for the movement of people, goods, and knowledge between planets and star systems. Even with these advancements, physical separation and time delays will encourage the development of autonomous colonies capable of self-governance and local problem-solving. Fostering innovation and resilience, cultural evolution will accompany physical expansion. Each colony will develop distinct traditions, art forms, and social rituals inspired by the alien landscapes they inhabit. Stories, music, and visual arts may reflect planetary features such as the color of skies, the behavior of native geological phenomena, or even imagined ecosystems. Language itself may evolve, incorporating new terms, concepts, and symbolic references unique to the experiences of life beyond Earth. Through culture, humans will maintain identity while embracing novelty, fostering a shared sense of belonging despite spatial separation. Education and knowledge dissemination will be crucial to sustaining interstellar civilization. Colonists will need extensive training in science, engineering, medicine, and social management to address the challenges of life on alien worlds. Continuous learning programs will combine Earth-derived knowledge with local experimentation, ensuring that each generation is equipped to maintain and advance colony operations. Education will also serve as a cultural bridge, preserving connections to Earth while encouraging innovation, critical thinking, and cross-colony collaboration. The ethical dimension remains central to humanity's long-term trajectory. Colonists must continually evaluate the impact of their actions on alien environments, potential life forms, and the broader interstellar community. As settlements grow, governance frameworks will need to ensure equitable access to resources, prevent exploitation, and promote justice. Ethical reflection will guide decisions regarding terraforming, resource management, and technological deployment, ensuring that expansion does not compromise moral principles or environmental integrity. Scientific exploration will continue to drive cultural and technological development. Colonists may discover new planetary phenomena, unknown minerals, or even previously unseen forms of life, expanding humanity's understanding of the cosmos. Interdisciplinary research, combining physics, biology, geology, and social science, will provide insights into both the universe and human adaptability. Scientific discovery will not only support survival and technological advancement, but also inspire philosophical reflection, creativity, and wonder. As human presence spreads across the stars, the very notion of home will evolve. Earth will remain the cradle of civilization, a source of identity, culture, and heritage. Yet home may increasingly encompass multiple worlds, each offering unique experiences, opportunities, and challenges. Colonists will navigate the tension between attachment to Earth and immersion in new environments, creating a multidimensional sense of belonging. This expanded concept of home may foster a more inclusive, interconnected, and resilient human identity, capable of thriving in diverse contexts. Ultimately, humanity's cosmic future is defined by both ambition and responsibility. The decisions made today regarding exploration, colonization, and technological development will shape the trajectory of civilization for centuries or millennia. By integrating science, technology, ethics, and culture, humans have the potential to create flourishing societies across multiple worlds. The vision of life beyond Earth inspires curiosity, creativity, and cooperation, reminding us that exploration is not merely about survival, but about realizing the full potential of human experience in the universe. This long-term perspective emphasizes hope and possibility. While challenges abound from environmental hazards to technological limitations and ethical dilemmas, human ingenuity and adaptability remain our greatest assets. Colonization, scientific discovery, and cultural evolution together represent a profound expansion of what it means to be human, allowing us to embrace the unknown while preserving the values, knowledge, and creativity that define our species. In this unfolding journey, each new colony, research mission, or technological innovation adds a chapter to the story of humanity among the stars. Future generations will inherit a legacy of exploration, responsibility, and imagination, shaping not only their lives but the very definition of civilization. The dream of inhabiting other worlds becomes more than a possibility, becomes a shared aspiration, a collective endeavor, and a testament to the enduring human spirit. As we conclude this exploration of humanity's potential future beyond Earth, it becomes clear that the journey ahead is as much about imagination, ethics, and culture as it is about science and technology. The dream of living on other planets is not merely a technical challenge. It is a profound reflection of our curiosity, resilience, and desire to expand the boundaries of human experience. Each innovation, discovery, and ethical decision we make today sets the stage for the generations who will walk on alien soils, gaze at unfamiliar skies, and call new worlds home. The vastness of space reminds us of our humility, even as it ignites our ambition. Planets with harsh climates, distant exoplanets orbiting alien stars, and moons bathed in faint sunlight challenge our ingenuity. Yet in these challenges lie opportunities for growth, creativity, and connection. By embracing sustainable practices, ethical stewardship, and collaborative exploration, humanity can thrive across multiple worlds while preserving the values that define us. The lessons learned in the cosmos will deepen our understanding of life, the universe, and ourselves. Every colony, every space mission, and every technological breakthrough contributes to a tapestry of human progress woven across the stars. The future is not predetermined. It is shaped by the choices we make, the collaborations we foster, and the ethical principles we uphold. The decisions regarding resource management, habitat design, environmental protection, and cultural preservation will determine whether life beyond Earth flourishes or falters. By acting responsibly and thoughtfully, humanity can ensure that the dream of interplanetary life is realized in a way that is sustainable, inclusive, and morally sound. As you listen to this narrative, perhaps in the quiet of night or during a moment of reflection, imagine yourself among the stars. Picture colonies under distant suns, communities thriving in harmony with alien landscapes, and future generations learning, creating, and dreaming. Let the possibilities inspire wonder and curiosity, reminding us that exploration is both a privilege and a responsibility. Thank you for joining this journey into the future of human habitation beyond Earth. Whether you are a student, a scientist, a dreamer, or simply a lover of the cosmos, your curiosity fuels the imagination that makes these visions possible. As we continue to learn, explore, and innovate, remember that the story of humanity among the stars is not only a scientific adventure, it is a collective dream, a testament to the enduring spirit of discovery, and a call to act with responsibility, creativity, and hope. May your imagination continue to soar, and may the stars always guide your curiosity. As we reach the final chapter of this exploration, it becomes clear that humanity's odyssey into the cosmos is not simply a story of technology, planets, or distant stars. It is a story of curiosity, resilience, and the unyielding desire to expand the boundaries of what it means to be human. For millennia, humans have gazed at the night sky, imagining worlds beyond our own, wondering if life exists elsewhere, and dreaming of what it would be like to walk upon alien soils. Today, those dreams are no longer confined to imagination. They are slowly becoming reality through science, innovation, and collaboration. The journey from Earth to the stars is a tapestry woven from countless strands: scientific discovery, engineering achievement, ethical reflection, and cultural evolution. Each step we take, whether sending robotic explorers, building orbital habitats, or investigating exoplanets, adds a thread to this tapestry, creating a picture of humanity as both ambitious and responsible, adventurous yet thoughtful. The Odyssey is not without its challenges. Harsh environments, distant horizons, and technological limitations test our ingenuity and resilience. Yet, with each challenge comes the opportunity to grow, to innovate, and to redefine what is possible. In reflecting on the human pursuit of life beyond Earth, we recognize that it is driven not merely by survival or expansion, but by the profound human need to explore, understand, and connect with the universe. Space is vast and often unforgiving, yet it offers lessons about patience, collaboration, and perspective. It reminds us of our shared fragility, the preciousness of life, and the interconnectedness of all things. Every mission, every research endeavor, and every colony embodies the hope that humans can thrive not only on our home planet but across multiple worlds, while preserving the wisdom and values that define us. The Odyssey also invites us to consider what it means to be human in an ever-expanding universe. Colonies on Mars, moons, or distant exoplanets will not only test our survival skills, they will challenge our social structures, ethical norms, and cultural identities. Communities will need to develop governance systems, shared ethical frameworks, and sustainable practices that honor both human needs and planetary integrity. These experiences will shape new forms of human society, providing opportunities to innovate in ways that were never possible on Earth. The cosmos, in this sense, becomes both a classroom and a mirror, reflecting the best and most aspirational aspects of human nature. Interstellar exploration also encourages a renewed sense of humility and wonder. As we venture further from Earth, encountering alien landscapes, new phenomena, and perhaps even other forms of life, we confront the enormity of the universe and the limits of our understanding. Yet it is precisely this vastness that inspires creativity, philosophical reflection, and a profound appreciation for life. Humanity's expansion is not a conquest of space, it is an ongoing dialogue with the cosmos, a journey in which observation, learning, and respect are as important as exploration and innovation. Technology, of course, remains a central pillar of this journey. Advanced propulsion systems, life support infrastructure, and artificial intelligence extend our capabilities, enabling us to reach places once considered unattainable. Biotechnology, sustainable agriculture, and habitat engineering allow humans to adapt to environments radically different from Earth. But technology alone is not enough. Its true power is realized when combined with human imagination, collaboration, and ethical responsibility. Together, these forces enable us to envision and create thriving communities among the stars, where curiosity, ingenuity, and resilience define daily life. The conclusion of this odyssey is not an ending, but a continuation. Each discovery, each mission, and each new settlement represents a chapter in a story that spans centuries and potentially millennia. Humans are not merely traveling to other planets. We are evolving our understanding of life, society, and the universe. We are learning to balance ambition with stewardship, innovation with ethics, and survival with creativity. This journey is ongoing, and its ultimate shape depends on the choices we make, the knowledge we gain, and the values we uphold as you reflect on this journey. Consider the role of imagination and hope in shaping the future. The human odyssey into space is fueled as much by dreams as by scientific calculations. It is propelled by curiosity, driven by collaboration, and sustained by the desire to understand our place in the cosmos. By embracing this spirit, humanity can continue to explore, adapt, and thrive beyond Earth, ensuring that future generations inherit not only new worlds, but also the wisdom and values necessary to inhabit them responsibly. In the end, the human odyssey is a testament to the enduring spirit of exploration, the capacity for innovation, and the commitment to ethical stewardship. It reminds us that the universe is not merely a backdrop for human activity, it is a partner in our journey, a canvas for our creativity, and a source of inspiration for all who dare to dream. As we bring this journey to a close, it is important to reflect on what the Odyssey into space truly represents. It is more than rockets, colonies, or distant planets. It is the manifestation of humanity's deepest aspirations, the desire to explore, to learn, and to grow. Every discovery, every technological breakthrough, and every mission contributes to a legacy that extends far beyond our lifetime, inspiring future generations to look up at the night sky with curiosity, hope, and courage. The human odyssey continues because we are inherently explorers. From the earliest voyages across oceans to the first steps on the moon, humans have always sought the unknown, driven by a combination of curiosity, necessity, and imagination. Now, as we contemplate life on other worlds, we extend that legacy into the vast expanse of the cosmos. Our journey is not just about survival, it is about thriving, understanding, and creating meaning in environments once thought inaccessible. Every challenge we face, harsh climates, distant stars, and uncharted worlds, becomes an opportunity to innovate. Life beyond Earth will demand resilience, collaboration, and ethical responsibility. Colonists will need to adapt physically, socially, and culturally, developing systems and communities that honor both human needs and the integrity of the environments they inhabit. This process will teach us more about ourselves than any exploration solely of other worlds could, about our values, our creativity, and our capacity to care for each other and the universe. And yet, despite the vastness of space, this journey is not solitary. It is shared. It is collective. Every scientist, engineer, thinker, and dreamer contributes to the human narrative, shaping the possibilities of life beyond Earth. Every idea, every experiment, and every conversation helps build a future in which humanity can flourish across multiple planets, enriching both our understanding of the universe and the depth of our human experience. So, as you listen to this, whether awake in curiosity or resting in quiet reflection, imagine the possibilities. Imagine colonies thriving under distant suns, cities crafted in harmony with alien landscapes, and communities learning, creating, and dreaming together. Let these visions inspire wonder, provoke thought, and remind you that humanity's journey has only just begun. Thank you for joining this exploration of human habitation beyond your curiosity. Imagination and willingness to envision the impossible are what make these dreams meaningful. As we continue to explore, learn, and innovate, remember that the story of humanity among the stars is not only about science, it's about hope, responsibility, and the enduring spirit of discovery. May the stars continue to guide your imagination, and may the future always feel within reach. The human odyssey continues, and we are all a part of it. And with that, our journey through the possibilities of human habitation beyond Earth comes to a close. We have traveled from the dreams of our ancestors gazing at the stars, through the scientific and technological advances that make space exploration possible today, to the philosophical and ethical reflections that will guide humanity's future among the cosmos. We have imagined life on distant planets, the challenges of building colonies, the wonders of interstellar culture, and the endless opportunities for growth, creativity, and discovery. The cosmos remains vast, mysterious, and full of potential. While Earth will always be our home, the universe beckons us to explore, learn, and imagine what lies beyond. Each discovery, each mission, and each step we take brings us closer to turning dreams of interplanetary life into a tangible reality. It is a journey of resilience, ingenuity, and hope, one that reminds us of our shared humanity and the enduring human spirit. Thank you for joining us on this incredible journey. Whether you listened while resting, reflecting, or simply dreaming, your curiosity has traveled alongside us. If this exploration has sparked questions or inspired wonder, continue to look up, imagine, and seek knowledge. The story of humanity among the stars is ongoing, and each one of us has a role to play in shaping it. Remember, the human odyssey continues, not as a destination, but as an ever-unfolding adventure. The universe awaits, filled with possibilities, challenges, and discoveries yet to come. Keep dreaming, keep exploring, and let the stars guide your imagination. Thank you for watching, and may your curiosity always reach beyond the skies.